Good morning, everybody. You can't imagine how I am happy to open this conference. I'm not going to list all people who contribute to organize this wonderful conference. Just to mention Dean of our school, Professor Andrei Rygorodsky, and further I'm going to read, since the list of essential supporters may be too long. Fuad Aliskerov from National Research University, High School of Economics. Daniel Berendt, Ben Gurion University. Konstantin Vorontsov, Lomonosov State University. Alexander Gasnikov, Moscow University of Physics and Technology. Me, Boris Goldengorin. Boris Kovalerchuk, Central Washington University, United States. Igor Krasikov, Moscow University of Physics and Technology. Boris Krokhin, Moscow Institute, University of Physics and Technology. Vladimir Makarenkov, University of Quebec at Montreal. Vladimir Matyukhin, Moscow University of Physics and Technology. Boris Mirkin. Without Boris, it is just impossible. Everybody, I hope, follow. National Research University, High School of Economics, University of London. Panos Pardalos, University of Florida. Oleg Polin, Moscow University of Physics and Technology. I mentioned our Dean Andrei Rygorodsky, Moscow University of Physics and Technology. Fred Roberts, Rutgers University. Trevor Fenner, University of London, and Margarita Shevtsova. Please applause to all people who really supported and make this conference possible. And I would like to express my warmest greeting to Professor Boris Mirkin. And at this moment, I hope we will enjoy today the whole day. And my congratulations to everybody, and thanks that you have found time to contribute to this meeting. Thank you very much. Our next speaker will be...
Свою глубокую благодарность за организацию этой конференции самому Борису Исаковичу и его руководству, прежде всего, конечно, в лице кафедры, руководства кафедры, значит, которая вот выделила и помещения, и средства, и прочее. Это очень трогательно на самом деле. Я почему тут это говорю? Потому что я не уверен, что у меня будет возможность вот так официально поблагодарить руководство, а в конце концов именно оно определяет наши возможности и, значит, частенько даже само существование. Я не уверен. Один из моих боссов, он всегда смеется надо мной. Я говорю, я хорошо помню порядки Советского Союза, и я придерживаюсь этих порядков. Пока что ни разу мне никто не наказал за это. Поэтому моя гипотеза, что нынешняя Россия в каких-то аспектах не сильно отличается. И вот с этими словами все-таки наука должна продолжаться. К сожалению, может быть, мне в одно слово, да, что я вижу, на самом деле, я вынужден согласиться с покойным Олегом Ивановичем Ларичевым, который меня очень поддерживал всегда. И когда я вернулся из 20-летнего отъезда центром научным, он мне сказал, все, наука в России кончилась. И я был очень, как сказать, я был значительно моложе и значительно более оптимистичен тогда. И, в общем, я возразил но он был, никакие мои возражения не действовали. И сейчас я вижу, что действительно какие-то у нас серьезные есть проблемы. Недавно я слушал обзор публикации вот в нашей области. Оказалось, что Россия на последнем месте из примерно 80 стран. Включая всю Европу, даже такие маленькие страны, как Словакия, оказывается, дают больше вклад в литературу, чем Россия. Ну вот те, кто здесь присутствует, это, конечно, наша надежда и опора нашей науки в этой области. И я надеюсь, что эта конференция послужит делу не вымирания науки. Спасибо большое.
Applied discipline. So the research, you probably know some or all of these wonderful books published by Professor Mirkin, starting with this, unfortunately, the resolution was quite poor. This problem, the first book, which was extremely popular in Soviet applied mathematics, was like fresh air among classical scientists dealing with differential equation, calculus, probability theory. Today I'm going to speak about one notion introduced by Professor Mirkin, namely the notion of Biclustering, also known in literature as co-clustering, and is usually referred in the literature as proposed by Boris Mirkin. And indeed, could you please minimize? Indeed, the first paper on the clusters was that of 1978, co-authored with Pyotr Rostovtsev, where the concept of a pair of most tightly related attribute subsets was first mentioned in the analysis of sociological data. And then, properly determined by B-cluster and even tree-cluster, like in three-dimensional data, these terms were introduced in the famous book of 1996, where B-clustering refers to simultaneous clustering of both row and column sets in a data matrix. B-clustering addresses the problem of aggregate representation of the basic features of interrelation between rows and columns as expressed in the data. So here we see the main idea. B-cluster is not one-dimensional thing. You need to have two components, and you cannot catch B-cluster with one hand. You need at least two hands. On the one hand, you have rows, and on the other hand, you have columns. So I think this idea is quite clear now, but I would say that the notion of the clustering was specialized in many different ways. There is a very nice, little bit old review. Probably there are more recent reviews, but this one is worth reading. Madeira and Oliveira, the clustering algorithms for biological data analysis. So, some theoretical problems are discussed as well. For example, one of the most used models of the cluster is the cluster of epsilon similar values, defined as an inclusion maximal submatrix of numerical matrix, such that for any pair of its entries, the difference of their values is at most epsilon. In the same way, clusters of higher dimension, 3, 4, and so on, are defined. It's not square submatrices like cubic, hypercubic, and so on. And here we come to one specialization of the cluster called formal concept. consider this simple example with objects in rows and attributes in columns. Attributes are binary. And here you see, I would call this a rigid bicluster. The pair 3, 4, rows 3, 4, and attributes PC, a maximal bicontainment submatrix filled with crosses. You cannot extend by any row or column without getting a gap. Yeah? If you try to add 2, then you get a gap here in for the attribute B. Inclusion maximal submatrix filled with crosses. And it's called a formal context by the founder of this direction, Rudolf Wille, who passed away years ago. But this has a very long history, even in philosophy, in European science, in Logique de Port-Royal, written by Antoine Arnaud and Pierre Nicole. They introduced what is a concept, following some Aristotle ideas. The concept has extent and intent, объем и содержание. Понятие есть объем и содержание. And they noticed this reverse relation between extent and intent. The larger the extent, the smaller the intent. Чем больше объем понятия, тем меньше его содержание. And then Évariste Galois introduced a couple of relations, a couple of mappings between fields of polynomials and groups of automorphisms, which were later, in the 20th century generalized to abstract Galois connections. And here there were wonderful works of Birkhoff, Ore, Vladimir, and finally Rudolf Wille gave a nice interpretation of what makes a pair of Galois connections. Actually introducing a formal model for the idea stated in the 17th century by Arnaud Nicole in Logique de Port-Royal. Here it is, in formal terms, we have a subset, we have a set of object G and attributes M. Before dying, Rudolf asked us to use German Gegenstände und Merkmale. So I follow this last code and use these letters for objects and attributes. And they make, and here we have two mappings from the power set of objects to power set of attributes, and from the power set of attributes to the power set of objects. The phi of A for a subset of objects A gives all attributes common to objects from A, and for a subset of attributes B, C of P gives you the set of objects that share all attributes from B. They have nice properties, anti-monotonicity, which were noticed in the 17th century in Logique de Port-Royal. If you have a bigger extent, you'd have a smaller intent. For example, you have a concept mammalia, млекопитающие. The extent are all animals of this kind, and intent is their common property. So if you take another concept, say vertebrata, позвоночные, then you have a larger extent but smaller intent, because the vertebrata share less common attributes than mammalia. In the Darmstadt school of Rudolf Wille, they replaced this thing C with one prime notation, which is slight abuse of notation because these are two different mappings, but this makes you rarely mix them in your mind, but the notation becomes much more elegant. So the set of attributes is called extent. The set of the set of objects is called extent. The set of attributes is called intent of the concept AB if A prime equals B and B prime equals A. So on a matrix, this means exactly a submatrix filled with crosses, which is maximal by inclusion, not by size. Necessarily, not by size, but inclusion. There are numerous applications in gene expression analysis, sociology, natural language processing, software engineering, thousands of papers. I would mention them now. We have not much time, but rather to discuss mathematical ideas. So concepts are partially ordered by relation of generality. This concept is more general than this one because the extent is superset of this extent, and the reverse relation for intents. So like if we use the same example, vertebrata is more general than a mammalia, because all mammalia are vertebrata, but the common attribute of vertebrata is a subset of common attributes of mammalia. So with this relation makes a partial order, and more than that, it makes a lattice, algebraic lattice, which means that every two concepts have infimum and supremum, which are uniquely defined, like you have it here. You have a diagram of this partial order. Also, Popov said that you shouldn't call it Hasse diagram because Birkhoff used it much earlier, but in literature it's sometimes referred as a Hasse diagram. There are nice properties of this prime and double prime operations. Double prime makes a closure operator, but this is not the main point today. Here I would like to stress that concepts make a sort of compression of object set and attribute set. Here we have equivalence classes of attribute subsets which have the same support in objects. So for this they have the same support 1, 2, 3, 4. For this this one element equivalence class, and these two elements have support 3, 4. But this red one refers to intent, which is the closed set of attributes, the maximal within this equivalence class, within respective equivalence class. This is maximal here, this is here, this is unique, and so minimal, and so on. So in a sort intense closed set of attributes make a compression of possible subsets of attributes with respect to data given by rows. There's a nice theorem saying that every lattice can be represented as a concept lattice. I will go into detail here. But this is a slide which is more important for us because it shows that the notion of concept is tightly related to dependency in data. Attribute implication A implies B holds when A prime is a subset of B prime. So each object having all attributes from A also has all attributes from B. The implications satisfy Armstrong rules, which are known in database theory for functional dependency. And actually they are sort of equivalent to Horn theory, a Horn sub-theory of propositional logic. So since we have these nice rules, we can think of implication bases, which are smallest subset of implications from which all other can be inferred using Armstrong rules. And there are efficient algorithm tools for computing the implication bases. Note. So here, implication can be visualized in a lattice. For example, we have implication B implies C, because whenever you have B, you have also C, and that is seen as the concept corresponding to B, this is 3, 4, BC, is below the concept corresponding to C. Yeah, this concept corresponds to B, because there is no concept with intent B, because B prime gives 3, 4, and 3, 4 gives BC. Yeah? So you can see this lattice as a compression of a Boolean lattice of all attributes, or Boolean lattice of all objects. In this, for example, in this two example, it has 9 elements, and the Boolean lattice of the power set would have 16. But in practice, the difference can be much, much larger. So the compression is much higher. Not only this, these implications are, I would call them deterministic dependencies, when you always have B if you have A. But in data analysis, you often have situations when you have B having A only with some probability. And this was captured in data mining under the name association rule. B is associated with A with confidence, which is actually conditional probability of B having A. And S is support, and says how many rows justify this dependence, this association. And what is the minimal representation of the set of association rules? Because everything can be associated with everything. Power set on the left side and power set on the right side. But a very nice and simple result shows that actually you can use the edges of the concept lattice diagram as a minimal representation of association rules. Note first that every edge is association rule. For example, C implies BC with probability 2 over 3. Yeah? BC implies BCD with probability 1 over 5. So in one direction and other direction can be proved by, I would go for this. So to store association rules, you need, you can use this diagram. This is the minimal representation of association. And if you want to make a threshold for support, considering only highly supported rules, you notice that support goes down from top to bottom, and you need to make a cut somewhere to get as much best supported patterns as you like. I leave this empty because I think no time for formal considerations, but you understand that this can be generalized to k-dimensional data as well. And here we have, for example, a theorem about reducing by clusters of similar values to 3 concepts. Not nice to read. And I'd rather show you this picture, which shows how the reduction goes. I here use theta instead of epsilon. But so here we have 2 biclusters of similar value for theta equal 1. Yeah. So the difference is no larger than 1. 3, 4, 3, 4. This is another bicluster of similar value with 3, 2, 3, 2. You cannot merge them. Yeah. But you can introduce another dimension, which is called the scale, interordinal scale, with binary attributes of this sort. And then biclusters become these parallelepipeds in 3-dimensional data, but now they are binary. And you have all FCA machinery for computing them. And as a byproduct, you reduce dependencies of this form both deterministic and probabilistic, two implications on binary attributes. The implications and basis of them can be efficiently computed by existing FCA tools. FCA stands for formal concept analysis. So with this, I'm approaching the end. We can, why this reduction is good? Because we can use the whole machinery developed in the domain of formal concept analysis. And although the number of concepts can be exponential and even hard to estimate, which is given by this result, I'll counting concepts, but there are polynomial delay algorithms for computing the concepts. And nice anti-monotonicity property of natural interestingness measures like support. Here I can show this with this slide. If you want dependency, let's say association rules with support higher than 1/2, you use your algorithm with polynomial delay. This one and this one. You can do this. You take k size and in the number of k concepts that you want to take as the best one. Yeah. So and dependencies on numerical data can be reduced to binary implications and computed by existing FCA tools. Yeah, in this. I'll show this in this way. So with this, I would like to finish and thank you for your attention and thank you, Boris, for being with us and stay along with us. Много и благое лето. Спасибо, коллеги.
Я хочу поблагодарить Сергея Kuznetsova за его поддержку этой конференции. Я забыл сказать, мы с ним отредактировали книжку, которую принято в издательстве «Спрингер». Ну, еще не поздно, там остался день-два. Если кто-то имеет что-то очень хорошее, давайте присылайте, я попробую это все опубликовать. Спасибо большое, Сергей.
Спасибо большое. Вопросы?
Вопросы?
Или мы не предусмотрели, да?
Предусмотрели, пожалуйста.
Да, вот если заинтересовала эта тематика, то могу вот предложить такую список литературы.
Thank you. Thank you very much. My talk is a kind of review of clustering as a classification activity. In machine learning, clustering is considered as a kind of auxiliary activity. I have a taxonomy of computer sciences created by the Association for Computing Machinery. And clustering never raises in there higher than second level from bottom, which is, in my view, is wrong. And I'm looking now at the possibility, what I'm doing, I want to move the slide. Вот это. Где стрелка? Здесь ее нет? Ну ладно, я буду так двигать. Thank you. So first I'll discuss a few words about what is classification, then about clustering viewed this way, and then of some current issues related to this presentation. So classification as a general form, I studied this when I was writing this book in Dimex in the Rutgers University of New Jersey. I spent a year or more studying what classification was. So it's a division of objects oriented for structuring the phenomenon under consideration, establishing relations between aspects of this phenomenon, and keeping knowledge. So I've written a book, first part of this book is devoted to the concept of classification. A few examples. Say in biology, we have here several lines showing development of considerations. So the current system is a very recent one, literally 20 years ago, due to the activities of Wooze, who understood that there is a specific class of living organism, archaea, which I have no time to devote to this. So the what was good about this classification? So the Linnaeus introduced a taxonomy over reproductive organs, which was very lucky because Charles Darwin could reinterpret this as a evolution, as a tree of life, evolution of survival of the fittest, and all this related to this. I have no time to discuss, but here we see how important this classification was. Other classifications created by Linnaeus, including mineralogy, also along these lines, had no successes because the reproductive organs of minerals were wrongly identified by him. Another example, which we as Russians should be very proud of, it's a periodic chart by Mendeleev that the structure of the elementary particles or atoms, I don't know if they are not elementary, then the structure allows to say a lot of physical and chemical properties of them. And this is another example where the structure of protein can tell you a lot of the properties of the activities of this. And one more example is Mark's classification that he claimed, in my view, wrongly, that there is a zero-sum game of two classes, capitalists and proletarians, and all this sociology and politics implied by this. So what is important maybe to point out that classification is not science. It was introduced by the great Aristotle and was thrown out at the very dawn of the sciences with a lot of other his speculations. This is why I think the greatest minds like Mendeleev and Wooze never had any chance to receive a Nobel Prize, because Nobel Prize is given for discovery of facts, of not the regularities. I also kind of came, after much thinking, came to conclusion that there are only 5 aspects of any process, and these aspects are structure, function, and history. If we are talking of the nature, and if we talk of the societies, then we should include here attitude and action, 2 other aspects. And so this The relating classifications I've given you already, that Mendeleev's periodic chart gives you relation between structure and function. In biology, the structure and function, and in politics, this at least Marxian taxonomy gave you structure related to attitude and action. Now so this was about the goal of classification. Now about the forms. I know basically only of 3 forms of classification. A taxonomy, which is mathematically a rooted tree. Typology, which is a partition or even just representatives of hidden partition, and ranking. And here I give examples like very popular currently league tables of universities and of scientists. And now I want to look at the clustering, how it works. So for me, clustering is a hierarchical classification. If a classification is done according to theoretical views over the universe, then clustering is done over data table, which is a very partial knowledge. And still we have a very similar 2 structures. It's a hierarchy, akin to taxonomy, and partition, which is akin to typology. And also clustering gives us one more structure, which is not considered in classification theory, one cluster structure, or single cluster. It's an original structure because when we apply this to data of relatively unexplored phenomena, we don't have all the classes. We have only one or few, and this is what we can explore. About ranking, this is a very different matter. That ranking is part of what is considered decision making, not data analysis or statistics. So in decision making, there are very different approaches. And I was trying to kind of reconcile, to put ranking into the clustering perspective. And a few words about this. So this is how the problem looks like. Here I have a data of about 2006. I've taken from a book about biggest cities in the world. And here we have 2 features: housing, which is the price of a 3-star hotel, 1 night, and food is price of McDonald's burger. Burger, is it called Mac? I cannot remember, unfortunately. Big Mac, yes. Thank you very much. Price of Big Mac. So when we look at this, I've taken 10 largest cities, and clustering is on the left part. So according to the similarity, we can see that Copenhagen is a unique position. It's tremendously expensive over food, and not that expensive over housing, unlike the Moscow, Tokyo, and New York, in which housing is extremely expensive, but the food is much less so. When we look from the position of stratification, then the stratification is much different. It is on the right. So we should draw a line, an axis, along which, not along, orthogonal to which are stratas going, and then London and Copenhagen will go into the same strata. But Sydney and Beijing would go into the middle, in medium strata, not in that cluster which is on the left part. So this stratification is a bit different activity. I made a criterion similar to, 2K means 1. So how do, okay, I did something wrong. Yeah, okay. So in the bottom part is this criterion that we analyzed with my PhD student, Michael Orlov, who successfully defended his PhD, and we found wonderful results over this. Unfortunately, neither myself, not anybody, nor anybody else would pick this up, so it's basically this direction I consider is dead. Now about classification goals, how they are reflected in the clustering. The structuring is exactly the goal of clustering. So it's predominantly clustering is doing structuring. About establishing relations, so far clustering is used tremendously little. Very few projects relate to this. As to the forming and keeping knowledge, I think it's not time. Time has not come yet. We have very rare attempts at automatic building taxonomies from text collections, not quite successful, but this is an area of current activity of few people. My own attempts in this direction, that when I was head of a department, of a laboratory for data analysis, then we introduced the concept of relative grouping in our program system, and it did work. Unfortunately, it's all disappeared, including the main person who did it, this Peter Rostovtsev. He died 20 years ago, so it's all gone. And in that institute, I think this activity is not going anymore. With respect to relating gene evolutionary trees with the species evolutionary tree, this activity is still existing, including my own attempts. It was a model developed, it's called Mirkin Muchnik-Smith. But to me, it's a little bit too formal, and as well, there are maybe a few dozen papers published, but no real development. So I'm turning now to the simplest form, the last one about partition looked from the view of another partition of the same set. This, my first publication in English was in the journal The American Statistician, and currently I'm trying to compile another paper to the same journal with some kind of specification of this, because not too many people are looking. And I'm going to, how much time do I have? 10 minutes? Let me check. So I'm at 11:55. Okay, so I have enough time. Thank you. So this is the problem. Partition R interpreted in terms of partition S of the same data set. So the major tool here is what the people call Pearson chi-squared. Pearson, I'll speak about him if you. I have somewhere picture in my slides. So this chi-squared basically is looking for statistical independence. It considers there is no association when this table shows statistical independence, and the index by Pearson measures this. He has proven a beautiful theorem that allows us to test statistical hypothesis of independence, but nothing else. There is no way. Oh, here all the theory is expressed. I don't want to dwell on this. I have somewhere. No, I don't. No, I don't, unfortunately. There is a paper, a recent paper called, so chi-square shows that the features are interrelated. So what? Unfortunately, this paper fails to explain what to do next. There are citations of 4 different approaches, what to do. In each of them basically comes to, in my view, to nothing. It's just more computations, but no definitive answer. So what is exactly related and how much it is related if there is a relation? None of these 4 approaches gives us any. When I approach this from a very elementary perspective of interpretation of a cluster, so interpretation of a cluster in k-means. Cluster, multi-dimensional cluster, is characterized by its center. Center is a vector of the averages within cluster averages of features. So you take this vector and relate it to the grand mean vector, to the mean over not this cluster, but the entire data set. And this is what you basically analyze, the relative differences. And then you apply this to categories, dummy categories, quantified, so because 0, 1. Then the average is basically is the frequency, the probability of this category. And the center, within cluster center, is conditional probability. So the relative difference come to what is put here as Q, Q in below a coefficient that we introduced, myself and this Peter Rostovtsev back in the 70s, to analyze sociology data. In our day of sociologist data, all features were almost independent. So the common measure, the conditional probability, did not work at all. So we came up with this index, which I called the relative increment of probability. When I came to the United States with this title, Relative Index of Probability, and abbreviation RIP, my host, Phipps Arabi, late Phipps Arabi, he said to me, should not use it. I said, why? He said, no, just don't, change it somehow. I changed. But later, while sitting in Rutgers University, I discovered that a bit earlier, Kotlyarov, the founding father of statistics, Adolf Kotlyarov, a Belgian statistician, introduced this already in 1834 in his memoir. So this was quite a discovery. I was real happy. here you have a picture, and as well as Pearson. Unfortunately, Pearson is non entity anymore. The University College in London, I was sitting just next to this building. It had a Pearson building. Not anymore. Pearson name is erased because he was his views, philosophical views, contradict to the current liberal values. So everything related to the name of Pearson in the United Kingdom is erased, as well as the many monuments in the United States have been erased because they were owning slaves at that time. And to a Russian person, this is a little bit difficult to understand. So what I found out basically, that this beautiful concept of Pearson coefficient, in fact, that this is a rather complicated formula, in fact can be derived with elementary considerations with no statistical independence in mind, just as the average of these Kettler index values. And this gives me a real instrument. So this decomposition gives me two things. First, it gives me operational interpretation of chi-squared as an association measure. In the textbooks in statistics, they say the chi-square is not a measure of association. It only can be used to test statistical test. So I give it, it's basically, it shows increase in probability of categories of one feature when we learn the category of the other feature. And also natural measure of local associations. I'm preparing now, I have prepared a paper for a similar event. A friend of mine from Canada gets 85. Nishisato, a Canadian statistician. So here I give you an example how it can be used for the analysis of relations. Here is a survey which is very relevant to us statistically, politically, because it gives us opinions of voters in the United States. It's about 30,000 people were asked by a very respected organizations what was their income. 4 groups of income. The first group is 30,000 or less. The fourth group is $100,000 or more. So first group is poor and fourth group is rich. And columns relate to voting behavior. Do they vote for Republican? Do they vote for Democrats or undecided? Undecided. And the value of chi-squared is absolutely negligible and shows that there is no relation between voting and income. But when we look at the Kettler indices, we see a little bit different picture. We see indeed that voting for Democrats has nothing to do with income. It's just the same, the last column. There are small numbers here. But for voting for Republicans is quite meaningful. If you are poor, you are 30% less inclined to vote for Republicans. If you are rich, you are 20% more inclined to vote for Republicans. So this is elementary considerations give us a very natural interpretation of the contingency table. So my conclusion, the view of clustering via classification enriches this area of clustering. You kind of get a picture what should be done, what has been done, and how it should be. Gives directions for novel developments, may bring forth unexpected results, and the last about this, the contingency table business is not complete and can be enhanced with effective, however simple, tools. Thank you very much. Oh, here is some references that I was citing while speaking.
Any questions? No questions. Let me send again.
Hello everyone, and thanks organizing committee. Today I'm going to talk about the method which I proposed. Well, not fully successful, but still it works in some occasions. And I titled today's talk as classification using marginalized maximum likelihood estimation and black box variational inference. Okay. So, can I continue or?
Yes,
Okay. So, I'm going to give you a very brief introduction of the black box variational inference. I'm going to explain the essence of the proposed method, sharing the experimental setting and the results over the real world, and if time permits, synthetic data set. And I will draw conclusion and explain the future works. So originally, the recipe for black box variational inference is what we can see. If I can show it with well, how can I show the laser? Okay, so what we are see here in the left hand side of the screen, that on the top, the problem in classical VR recipe. We were integrating over two distributions and then taking derivative and optimizing the objective function. In the newer recipe, which was proposed with a group of researchers from Google research group, Rangas and his colleagues, they switched this integration and taking derivatives, and then the rest of recipe is the follow. And this brings several simplicity, and this is one of the reasons they propose this switch. And the reason, I essentially relied on this principle, so taking derivatives and integrating and then optimizing the black box, optimizing the objective function. And why it is called black box? Because we don't specify any specific normal distribution. We can have just merely a bunch of data and a neural network and try to feed it through the a slightly modified version of classical conventional learning methods, actually. So to be a bit more specific, we define the inputs as set X, which usually in my work I consider them as a v-dimensional vectors, and the capital Y represent the corresponding target values, which for the classification task, this work, I convert them to one-hot encoded vectors. And by assuming that, so this is probably the main point of this talk. I assume that during the generation of data points, there is a set of existent variables, Z. It could be equal to the number of classes here, or we can play with this actually. How we should determine the set of hidden variables. And just pursuing the principles of maximum likelihood estimation, it is not hard to show that the equation 1 can be derived. And for optimizing this equation 1, you know it better than me, there are a lot of optimization methods. For this work, I adopted black box variational inference as I'm going to explain. However, optimizing this equation, our proposed objective function is not straightforward, and instead of doing that, I propose to optimize its evidence lower bound, or so-called elbow. I'm sorry. So, well, probably I should not. I don't know. I will try to make it as technical as possible. But this is the definition of elbow. So, for two given distributions Rx and Yx, here I showed the distribution, the definition of elbow, and by just recalling this definition of elbow, we can show, and applying the Jensen equality, we can easily obtain the equation 2b here in the lower part of the slide. So it's just a bit of probably basic math, which I'm pretty sure all of you can do it by far better than me. And then we obtained a new objective function, which I just repeated on the top of the this slide for the convenience. And now we can just apply the optimality condition easily. First order optimality condition, that is taking derivatives from this one, and equation 3e. I just chose the corresponding equations as to the paper just for the convenience. And this equation 3e can be optimized using Monte Carlo gradient estimator. And this work, to be more precise, in this result which I'm going to show you, I use the so-called variational inference, reparameterization trick, which is quite familiar in the work of the variational autoencoders by Derek. I forgot his name, but this is one of the first applications of the reparameterization trick. Here, I also Kingma. Sorry, I mentioned the reference here. So I pursued this method, and if we want to be a bit more specific how we can pursue this method, we can assume that there exists a transformation rule such that we can draw the samples epsilon I for n data points from this simpler and parameter-free distribution, which is indeed independent of the theta, the parameter of our model which we are trying to derive. And then by applying by using a deterministic path t epsilon I and theta, so we can transform our hidden variable zi, as I show here, is equal to t epsilon I and theta, and epsilon I is derived from our distribution, parameter-free distribution. And well, with this, let me give you an example to be more specific. So assume that we derive the epsilon from a normal distribution, normal and standard Gaussian distribution, and then with doing the location and transformation of epsilon, we can show that z is nothing but equal to epsilon multiplied by sigma plus mu, and then we can conclude that z is indeed derived from this normal distribution with parameter mu and phi. And what it brings us, this brings us to the point that we can replace the z in our equation with this deterministic function, and because we cannot compute the gradients of z because they are interactable. Sorry, I forgot even to mention it. And this is why we replace with the z with a reparameterization trick, actually. And well, with just replacing, we can come up with the equation 4b, and then applying the principles of Monte Carlo gradient estimator. So we just draw samples epsilon L number of samples, and then we evaluate the functions, our equation 4b, and then we compute the empirical means of these quantities actually. Just for the convenience, I named this equation 4b as G. So this is the just simpler notation of the Monte-Carlo gradient estimator, and we can summarize the process of this MMLE as follows. So it's just the slightly modified version of the stochastic gradient descent. So we apply M is the batch of the data set. We just derive a set of noises epsilon, and then the rest of the update is the same. And we continue this process until we converged. And well, the source code is also available in the GitHub if any of you is interested. So this is the essence of the parameter, and to test the efficiency of the proposed method, I compared the method with more algorithms here, but because of it would be very long, so I decided to limit the report with these three competitors: AdaBoost, conventional MLE with no marginalization, and the third work which I just mentioned as CLSP. Well, probably it's not a good name. Well, definitely it's not a good naming. Sorry for that. And well, I applied my algorithm and these three competitors on 4 real-world datasets: IRIS, MNIST, forest cover, and wine dataset. And probably I should mention that I applied this method on also, well, initially I proposed this method for imbalanced classification of outlier, imbalanced outlier detection. But since my affiliation changed, so I couldn't introduce those data sets which was devoted to that lab. And over there, I obtained quite better result than what I'm going to show. And I also just wanted to study the performance of algorithm over nonlinear data set like moon shape or different dimensionality of hypercube Gaussian distribution. And I used the Rokok as my metric. So here is the results. The last two, I must add that if I use linear activation function, I add the Li to my algorithms, and if I use ReLO, I added Re. So the last two rows are the proposed algorithm of mine, and well, we can see that it wins over 2 real-world data sets, and the result for forest coverage data set is also not bad. And over the Gaussian hypercube, conventional MLE wins most of the cases. However, the proposed method maximum marginalized maximum likelihood wins 2 cases when we have 2 informative features and 18 non-informative random features. So probably I should mention that these 2 plus 0 means that we have 2 informative features and no non-informative features. 2 plus 18 means that we have 2 informative and 18 noises, and so forth. So in these 2 cases, these algorithms win the competition, and overall the obtained results are quite similar, but I cannot say that it's a big victory. Well, I need to probably work more to understand how can I improve the results. It's competitive, but it's not. Here is the result for moon-shaped dataset in 2 cases, balanced and unbalanced. Again, the results are similar to other competitors, but I cannot say that, well, it didn't win, unfortunately. So, as a conclusion, I proposed marginalized version of the conventional maximum likelihood estimation. And I operate with two different versions, separating the activation function during the training process. The results appear to be valid, competitive, but I cannot claim that it's unfortunately very effective, although there were cases that the algorithm wins over the competitors. As for the future works, I see several future works. First of all, and probably the most important one for me, is to study the dimensionality of the hidden variables. How we should study the hidden variables. Should be just equal to the number of classes, or we can. This is something which is very interesting for me. Or applying the different transformation rules also can be of interest, instead of just the reparameterization trick. And well, of course, extending the list of competitors, and well, there are a lot to do, but let me finish with this, and thank you for your attention. If there is any questions, I would be happy to answer. Yes. Yes.
For your objective function.
Yes.
My question is that do you have any recommendations in any other optimization method to handle that function?
Well, actually, this is one of the future works which I need to investigate. At the moment, I cannot recommend anything else, unfortunately. But yeah, but in the paper, I at least cited 2-3 more methods for tackling, well, for optimizing the objective function. I can check it. At the moment, unfortunately, I cannot remember the names. But yeah. Yes.
Have you tried with the XGBoost? So how much the result differed?
Well, usually XGBoost gave us better result than AdaBoost, yeah, but not all the time. Yeah, usually it gives us better. Well, as I mentioned during my talk, I cannot say that it's very successful results, but well, it's still in progress, and I hope I can. Yeah, XGBoost usually gives by far better result than AdaBoost.
For outlier detection,
Mm-hmm.
detecting outlier is very much tough sometimes, because you need more experiments, because you cannot say that may not be outlier, but it's still.
That's true.
Outlier.
That's true.
What strategy taking for this?
Well, when I was working on this that specific anomaly detection task, one of the approaches which gives us good result. In addition, this algorithm works really good over those data sets, but I cannot share the result because of the changes of affiliation. But another algorithm which gave me good result at that specific task was to train just one, for example, what we were training an autoencoder on just the normal data set. And after that, for classification, we were giving a test set, and we were measuring the reconstructed output of the autoencoder with the normal distribution and abnormal. If the one which gives us the shorter distance for this test data point, we would use the same label for this. This gives us very good result instead of handling, because of the class imbalance. Usually we just learn one representation, and this was one of the good methods, and it worked quite good. Yeah, you're welcome. Thank you for your question. So, okay. Well, thank you, everyone. Finished earlier.
Thank you. Next.
Director of the school would like to say a couple of warm words to Boris Mirkin, and then your turn, you will continue, okay?
Excellent. Yes.
Thank you very much.
Да, ну, товарищи, с вашего... О, слушайте, тут заработал микрофон какой-то сам по себе. Вот у меня нет микрофона, а голос усилился. Как так? Ну, с вашего позволения, я говорить буду по-русски. Я умею говорить по-английски, но мне кажется, что мое выступление не нацелено на иностранную публику. Хотя могу, конечно, что-нибудь сказать и по-английски тоже. Вот, но для меня просто важно, что мы организовали в конце концов это мероприятие. В конце концов, потому что Борис Исаакович с ним пришел довольно давно, и мы сначала планировали его организовывать в другие даты. Думали, что это будет в конце декабря. Ну, не знаю, хорошо ли я поступил, перенеся это на конец января, или нехорошо, потому что, к сожалению, я все-таки не могу сказать, что здесь толпа народу. Но мой замысел был в том, что конец декабря – это конец света. Потому что вообще у всех отчетный период, а у нас тут еще была страда. Мы занимались защитами кандидатских диссертаций примерно 20 аспирантов, которые мерзавцы дотянули до самого последнего. То есть вот выбрали просто последние даты декабря, чтобы защититься в срок. Ну и, соответственно, в общем, целыми днями мы сидели и защищали этих аспирантов. Вот и Константин Вячеславович в этом активно участвовал, и Сергей Олегович тоже дистанционно, но очень активно напрягли мы Сергея Олеговича очень сильно этим. Вот, в общем, казалось, что там, это никак не организовать, поэтому решили перенести на конец января. Ну вот, не знаю, как надо еще пиарить среди студентов такие мероприятия. Вроде вся информация была выложена, но тем не менее как-то вот не очень много студентов, что жаль, потому что тут собралась, конечно, замечательная совершенно аудитория. Я этому обстоятельству очень рад. Ну и, конечно, я всячески поздравляю юбиляра, в честь которого, собственно, это мероприятие собрано. Мы его очень работы ценим, уважаем. И физтехшкола наша, конечно, славится решением задач нашими профессорами, нашими сотрудниками научными, к которым наш юбиляр имеет прямейшее отношение. Вот, поэтому я считаю, что очень здорово, что это произошло здесь, на площадке физтеха, в рамках физтехшколы прикладной математики и информатики. Вот, друзья, я прошу прощения, я, честное слово, сам все еще существую в ипостаси математика, не только административного работника, но у меня этих ипостасей 3. Я очень люблю читать лекции и делаю это повсюду. Вот вчера был, позавчера был в Липецке. Вот, а скоро поеду на Урал. Ну и в четверг начинается, собственно, семестр. Я буду читать обычные свои курсы, которые здесь читаю. Вот, и математикой я занимаюсь, но, к сожалению, очень много времени все-таки съедает организационная работа. Я директор ППМИ, и я сейчас побегу к ректору. Вот. Спасибо, да.
Я хотел бы лично вас поблагодарить. Ясно, что без вас ничего бы не было.
Спасибо.
Это для меня просто...
Спасибо большое.
Большая честь. Спасибо вам.
Ну, дай бог, хорошо. Да?
Там, к сожалению, студенты восприняли это так, что нужно заказывать пробы. И они, конечно, причем до 24 февраля. Вот, они просто не пришли.
Я не знаю, где это было так написано. Это Борис, что ли, сделал? Не Борис Исаакович, а Борис Трохин.
Нет, я написал, что те, кому нужен пропуск, закажите его заранее и приходите с паспортом. Но студентам не нужен пропуск.
Видите, вот
Сирийский студент.
очень досадно, да. Но как-то, видимо, не доглядели. Но мне кажется, что это нормально было написано, что если кому-то нужен, то напишите нам.
Я просто просил.
А я не знаю, Борис Исаакович, как было-то?
Ну вот как я
Они
сказал.
подумали, что им тоже надо стать.
Ой, господи.
Написано, что студентам ФПМИ крайне рекомендуется сходить. Очень интересная конференция.
Не, ну на ФПМИ-то мы и рассылку сделали, и в соцсетях это повесили. Ну как
Мне
еще?
потом одна студентка из из высшей школы экономики, сказал,
Мгм.
вы должны были объявить сертификаты выдать. Тогда.
Но сертификат я тоже подтвердил, что готов
Да,
подписать.
ну,
Да, да.
уже было поздно.
Сертификаты,
В
пожалуйста.
следующий раз. Да.
Ну, придется, да, такое вот случился некоторый.
Спасибо. Ничего, по-моему, всё
Дай
хорошо.
бог, да. Да, ну, нормально, на самом деле студенты настолько загруженные по жизни, что вот они сейчас на каникулах, а завтра, типа, послезавтра начинается семестр, да? И вот они считают, что последний день каникул надо посидеть дома, да? Ну, как-то так.
У них нагрузка в день.
Где-то 4 пары, 5
Или
дней.
пара.
Ну, нагрузка приличная.
Спасибо вам.
System and decision making, uncertainty and false is machine learning. Classification of machine learning algorithms designed to deal with a Byzantine or malicious data. In the next, I will explain what is malicious data. Interesting since realistic model the learning, for example, to address the issue of Byzantine data. And in this work, to handle the issue of using different approach, that of introducing the certainty level measure as a tool for a copying of corrupted data in item, and combine learning results in a new and unique way. Let's start. In present of Byzantine information or Byzantine data. Artifact may not a function of they should, or even act as inverse. Machine learning support adaptive internal structure, not balance rules and artifact. Seek for method to filter suspected data. It means we need to think about the idea how to remove suspicious data from the data set for the machine. So there are several new approaches to obtain classification certainty. And machine learning technique applied to online statistical data. Let's see this example, this figure, and understand what is Byzantine data. First, on the left histogram, we see in the green the histogram. For example, the label of the left side of this histogram is -1, and in the left side is it's labeled as +1, and in the side of the label is +1, the left side, we see here data that does not belong. Exactly here, we can see, for example, data that is not belong. This is we calling Byzantine data. Thus, the data that in this case contain n object real data, in which n are corrupted. And maybe it's malicious, maybe it's better. Better to identify suspicious data and reduce the influence of the Byzantine data. This approach assumes that we can separate clean data by procedure based on calculation of the mu and the sigma parameter of uncorrupted data. According to the sample limit term, 30 data items chosen uncertainty, which we call batch, can be used to define mu and sigma. First step, we try to find at least 30 clean samples with no Byzantine data, and we use n equal 30 as a cutoff point, and we assume that the sampling distribution is approximately normal. This is according to the statistic rule. And in the precision of Byzantine data, we should try to ensure that the set of 30 samples is not include any Byzantine data, any Byzantine item. In the case is similar to the case of shipment of n object real data, in which m is defective, Byzantine. The probability theory and statistic is a case of hypergeometry distribution that describe the probability that in a sample of n, this distinctive object draw from the shipment exactly n object are k object are defective. So the probability for selection k item that are not Byzantine is according to this equation p, you can see x equal k. We can see this equation of hypergeometry distribution. And for the clean sample, k equals 0, this equation will be x equal 0. We can see that no k here. In order to prevent the influence of the adversary on the estimation of mu and sigma, by addition the Byzantine data, we require that the probability in the equation will be higher than 50%, p greater than half. And according to the cutoff bound, we will obtain lower bound for the success probability of majority of n independent choice of 30 sample batch. By small number of batch sampling, we will obtain a good estimation for mu and sigma parameter for the clean batch. Thus, the ratio between n all sample and m the Byzantine sample that imply a probability to sample a clean batch that is greater than half is present in this figure. We see in this figure, and we see in y-axis is all sample, in x-axis is Byzantine sample, and we see the gap between the size of each axis. Thus, the ratio between n all sample and m is by 2%. For example, 20 Byzantine sample for every 1,000 sample. So if this Byzantine ratio is found by a new method, the probability that any other column in the dataset will contain a Byzantine sample is low. So our goal is to sample majority of clean batch to estimate statistic parameters such as mu and sigma of the non-Byzantine sample in the dataset. And the estimation of this parameter will be done according to algorithm 1. And I show now what is algorithm 1. Estimate statistical parameter. In step 1, we choose batch of n sample, b start time. In step 2, we compute mu and sigma for each batch according to the statistical law. And in step 3, get the histogram of all estimate of mu and sigma. It's meaning, for example, if I do it 1,000 times, I get 1,000 results from mu and sigma, and I can build a histogram. And in step 4, the median of mu and sigma, we believe will be clean. So this is the idea of algorithm 1. Algorithm 2, it talk about the new technique for remove suspicion data. In step 1, we divide the histogram into theta bins. For example, in this figure, we can see that theta equal 19. We count the actual number of the data item in every bin. For example, for x equal 117, the number of the item is 118. In step 3, we compute the number of data item in every bin by the integral of normal curve and compute the f. For example, for x equal 170, mu is 118, sigma is 16, the n is 8,019, and f equal 182. In step 4, if the ratio between f and c is higher than 1 plus psi, the data item of this bin are suspicious. For example, here we can see that ratio between f and c for x equal 117 is close to 1. So this bin is not suspect. And we do some experiment, and we see data set with artificial data is 100% accurate. If we add to artificial data some corrupted data, the accuracy of the machine learning, the classification of the machine learning is reduced to 78%. If you use our system and remove the suspicion data from the data set, the accuracy is not 100%, but is very, very high. So this is a good way to clean the data before we start to use with the machine learning. The next section of this work dealing with corruption of the existing data, single feature learning with certainty level. We continue consider the case where the part of the data in the feature is corrupted. Our goal here is to find the certainty level of every sample in the distribution in case where the upper bound on the number of the corrupted data item is known. This continuation of the previous, as a both part deal with a single feature, where the first deal with attempt to find the overflow sample, and the second cope is unsuccessful such attempt. Histogram of this sample is color green, where the black vertical line in the cross of the histogram separates sample with label plus and -1. And the label of Byzantine data have an invariant label with relation to the label of the non-Byzantine data item with same value. To achieve our goal, we describe a general method to bound the influence of the Byzantine data item. So algorithm number 3, find the centrality level. The centrality level zeta of each bin is calculated by the follow equation. L is a number of data items that are labeled and as -1. L plus 1 is a number of data items that are labeled as +1. N is a number of data items in the bin. And Xi is a number of corrupted data items. Step 1, take the training data set, sort the data sample according to the value, and create this histogram. Step 2, count the number of the sample in every bin, and count the number of the samples that are labeled +1 and -1. Step 3, find the centrality level of each bin, centrality level zeta of each bin in the equation, according to equation 1 and 2, and the assumption of on the size of this, on the size of the maximum Xi, for example, here is 8. So we can see we calculate zeta for every sample in, for example, bin, specific bin, for example, bin 117 or bin 171, and we calculate zeta for +1 and -1, and we assume that maximum Byzantine data in each bin is 8, not above 8. In general case, in which corrupted data are a part of dataset and can appear in two methods. An entire feature is corrupted, one option, and the second part of the feature in the dataset is corrupted, and the other part is clean. Note that there are several ways to corrupt an entire feature, including inverting the classification of dataset, selection a random data item, or produce classification inconsistent with classification of other non-corrupted feature. For example, we can see that here inside the histogram, we have corrupted data with a different label. And the black line is separate between label -1, label +1, and the corrupted data inside the histogram. method to bound the influence of corrupted data item. Our technique is based random forest with decision tree, where each decision tree that is created dependent on the value of random vector that represent a set of random column which chosen from the training data. Large number of trees are generated to create a random forest. After this forest create, each instance of from the training data set pass through this decision tree. Whenever a data set instance arrive to the tree leaf, each tree classification is compared with its class, plus or minus 1. When the classification and the class agree, the right instance of the leaf is incremented. Otherwise, the value of the wrong instance of the leaf is incremented. Thus, from single feature to several features, introducing the centered level as a tool, collaborative machine learning results, and we use with C4.5 decision tree as a test case. So this certain level based Borontsov decision tree, in step 1, we see the random vector are choosing from the training data. This is the example from the random vector, and this is the label of this sample. In step 2, using any decision tree algorithm to build a classification tree, that we can see here. This is based on these results. And each variable from the training data pass through this decision tree. Right and wrong classification are counted. For example, here we can see that this classification get right 30 times and wrong 1. Here is 20 for right and 10 and wrong. And the third is right 3 and wrong 5. Step 4, large number of this classification tree are generated. Each new variable from the test data pass through this tree, and we get a forest of results. The final classification of every variable will be determined according to classification. This is, what the decision tree so. If you came to some leaf, it means this is the classification of the tree, and right and wrong, and that are obtained from all three. It's meaning the decision is not only with the classification, it's classification with the certainty results that we get. The meaning, I will believe to this classification more than I believe to this classification. Because when I pass the training data set in this decision tree, I see that this leaf, in most of the case, he give good results. And here, in most of the case, he gave me wrong results. This is, for example, that we do on a real data. And we can see, for example, here, that this leaf I get 22 right and 0 wrong. And here, for example, this one, I see 5 right and 2 wrong. This is on the real data that we use. Over here, for example, I say 3 wrong, but 348 right. So algorithm 4 is identify and filter Byzantine data. First, select number of tree to be the generate. For example, K. K can be 500, 1,000 out of the trees that I want to create. In step 2, for K from 1 to bk per case, a vector theta k is generated where theta k represent a data sample select from for creating the tree, construct the tree by using decision tree algorithm. It's meaning now in step 2, I build a random forest. In step 3, each instance from the training data pass through this decision tree. And for every leaf, the number of instances that are classified correctly right and incorrectly wrong are count. Then the percentage of right and wrong classification are calculated. In step 4, each instance from the test dataset pass through this decision tree and receive classification. And in step 5, each new instance will receive results, classification right and wrong from the tree in the forest, and right and wrong percentage from all the tree are summarized. For example, sample 10 is classified by tree number 1 and node F5 as +1 with 90% correctness and 10% incorrectness. The final classification for each instance will be determined according to the difference between the total correctness, right classification for +1, and to the total incorrectness, wrong classification for +1, that are summarized for all three. This is important. This is the way that we can decide that we give, for example, a different classification if we can see this specific leaf is give us 100% wrong results. For example, if some leaf all the time give me wrong results, in the classification, the final classification, I can change his final classification, for example, from +1 to -1. And this is experiment and results. We can see when you use for a set image, some training set with accuracy majority void, as a random forest working, the pure random forest algorithm, we see that we get 88% success, and with accuracy run wrong, we improve it to 92. And we can see all the time that the results of the new technique is better than pure random forest. It's meaning that with this way, our random forest will be better. So this is results of the new algorithm, origin and corrupted data. Conclusion and future work. 3 methods dealing with corrupted data. Byzantine data items were added. Corruption of the existing data item, and several features, partial or entirely corrupted. The new idea for the classification process by using reputation of the source and learning algorithm that are based on the reputation of the data item in the recent post. So this is my talk. So if you have any question, I will be glad to hear. Oh, unfortunately, I cannot hear nothing. Can you send me what the questions?
Repeat, just a moment.
Thank you for your talk. I'm curious to know, how did you tune the hyperparameters of the random forest during these 4 versions of your algorithm you proposed?
We get the original random forest algorithm and code for the guys invade the random forest, law Breiman. He give us a code in Fortran, and the original code that he write, and we translate it to C++, and we got with this code. And this original code of Breiman, Leo Breiman, used for us to improve his technique and the results you can see here. It's not a Python or something. This is the original code of Breiman.
Yeah. Well, actually, can you by chance remember, for example, what was the number of estimators you used for one of your because I'd like to have some intuition about how the parameters of random forest changes when you use your method or before applying it. Do you have any such results reported? Or you can
this is a little bit old article. Okay. So I don't remember exactly, but I can check, if you send the email or something, I can check this issue.
Okay. Thank you very much.
I remember now exact results that I have.
Okay, thanks.
Thank you. Any more questions? We have one more question. Thank you.
Maybe the question shouldn't be addressed to you, the authors, Professor Dolev and Leshem, but the fact that corrupted data are called Byzantine I think is strongly politically incorrect. I think that Greek colleagues can be offended by this, and as we Russians supposed to be partly heir of Byzantine Roman Empire also, so this term sounds Hellenophobic and a bit Russophobic as well. So but maybe it was introduced earlier, but I don't support using this term for corrupted data. Thank you.
Okay.
Okay, thank you.
It's times that I hear this argue, I must tell you, but okay. It's it's something that belongs to the history, but
yes, I think so. It was introduced much more early.
Yeah.
I would like to thank you again. And my Hebrew is really restricted. Chaim Avra, Siat Chaim Metav Ichulai, Lyom Chulatcha. or in the language of your grandfather, sei mir gesinnt in a Größe dank dir. In Gibber Gries, Baron Daniel. Thank you again.
Thank you. Okay.
Dear colleagues, I hope you will hear me. And my name is Yakov Karandashev. I present Scientific Research Institute for System Analysis of Russian Academy of Science and also Rudan University. We, with my colleagues, did this work, and let me share to show you our results. So the topic of my presentation is anomaly detection with neural networks using a generator of anomalies. What's about? The problem that we considered is given us by our customer who manufacture full body scanners. It's Russian manufacturer based in Orel, and they asked us to make some optimization of the process of the images. What are the images? What is a full body scanner? It's a big box where you can come in, and this apparatus takes a photo of you, one photo in front, and this photo is taken in X-ray range of spectrum. It's different from maybe you know another scanner that usually used in airports, but in airports usually used millimeter wave scanners. But here is X-ray scanners. They are not so popular, but they have big advantages because they can look not only on the surface of your body, but also can look into your body. Of course, these scanners has some dangers, but really the doses of X-ray radiation is very small. Here you can see the comparison of the doses from various processes, natural processes or artificial processes, and as the manufacturer of this apparatus claims, the dose received by a body is 100 smaller than the dose from the typical I can't show typical lung X-ray. When you do medical observation in a medical center, you typically observe with X-ray your lungs, and it radiates you with a dose about 1 or 0.1 millisievert. And this apparatus of full body scanner is 100 smaller. So it's not really dangerous, and such apparatus can be used in they are typically used in I'm sorry, I forgot this word in English. В тюрьмах. По-русски?
все свои,
Нет, если это возможно, я с удовольствием переключусь.
потому что ну зачем?
Спасибо. А также на каких-то заводах, откуда нельзя ничего выносить. Вот. Но, в принципе, потенциально можно использовать в аэропортах, поскольку, как я сказал, дозы очень низкие, гораздо... Окей. Так, вот. Значит, что представляют собой данные? Данные — это одноканальные картинки в градациях серого. Вот здесь вот слева представлено изначальное изображение, то есть это TIFF, картинка в формате TIFF, 16 бит на пиксель. И что требуется? Да, я как-то пропустил это. Что требуется? Требуется находить все подозрительные объекты, не относящиеся к телу человека. То есть, чтобы человек ничего не пронес, ничего не вынес, ничего, ну, в общем, запрещенного. Вот. Сейчас этим занимается, то есть совместно с этими сканерами сидит оператор, который смотрит на эти картинки. То есть человек заходит, его фотографирует, и оператор смотрит на это изображение, применяет к нему различные фильтры, увеличивает, уменьшает, смотрит какие-то, в общем, подозрительные места. Ну, секунд, может, 10, 15, 20 у него уходит на то, чтобы визуально осмотреть это и пропустить человека. Вот. Соответственно, задача оптимизации, конечно, очень важна. И первая задача, которую мы поставили для себя, это, собственно, как с этими снимками вообще обходиться, потому что изначально на них ничего не видно, человек просто черный на белом фоне. Вот, естественно, нужно было как-то отфильтровать, поменять, может, контрастность, яркость, какие-то применить адаптивные гистограммы. Вот здесь вот показана процедура некоторая, которую мы для себя подобрали. Это несколько операций, которые приводят к тому, что, по крайней мере, на фото становятся видны внутренние органы, кости. Ну, то есть она не становится более градуированной, более приятной для визуального осмотра. Вот. А зачем нам это нужно было? Значит, мы рассмотрели эту задачу. Ну, то есть, что здесь является потенциально запрещенными, опасными объектами? Вообще задача изначально ставилась даже не так, а просто находить все, что не относится к телу человека. Вот здесь, скажем, видно на рисунке, что у него что-то на шее, какая-то цепочка. Также есть что-то в карманах, на руках, ну, там, на поясе. Вот, то есть все эти объекты необходимо автоматически выделить. И, собственно, мы... да, как-то мне за временем следить. Хорошо. Как мы решали эту задачу? Вот нам дали ее, мы подумали, ну, наверное, классический компьютер Vision, какую-нибудь нейросеть для компьютерного зрения мы вполне могли бы применить. Какую нейросеть? Ну, наверное, для сегментации изображений, поскольку здесь изображение, нужно на нем выделить какие-то объекты. Вот. То есть мы поставили задачу себе как сегментацию. И чтобы свести эту задачу к обучению с учителем, нам был необходим размеченный датасет. То есть нам нужно не просто набор картинок, картинок у нас много, нам дали сразу 1600 картинок, потом еще добавили 3000 снимков. Вот. Нам нужен размеченный датасет, и, собственно, мы это делали вручную с помощью Label.me. Я думаю, многие из вас знакомы с этой программой. То есть фактически человек вручную смотрит на эти снимки, уже визуально обработанные, чтобы было легче выделять вручную всякие подозрительные вещи. Вот. И, естественно, мы попробовали также сервисы, такие как Яндекс.Толока, на которые можно аутсорсить подобные задачи, то есть чтобы другие люди занимались вот этой ручной разметкой. Вот. Ну, по нашему опыту это оказалось не очень удобно, потому что, во-первых, нужно людей, походу, заставлять это делать, то есть как-то усложнять им задачу, потому что нужно за ними проверять. Вот, за ними нужно проверять, и то качество, которое они дают на выходе, ну, всякое бывает. Кто-то хорошо размечает, вот здесь пример на русском, здесь слайд. Ладно. Вот. А кто-то просто тыкает как бы вот более-менее рядом и все. То есть какие-то объекты выделяются не сильно хорошо. Вот. Но тем не менее, то есть с помощью Яндекс.Толоки, а также с помощью самостоятельной доработки вот моих коллег, мы разметили эти 1600 снимков и дальше начали применять обучение с учителем с помощью нейросетей. Вот. В качестве нейросети мы выбрали UNet. Почему UNet? UNet — это моя любимая вообще архитектура нейросетевая. Я ее очень обожаю, использую везде, где только можно. Она очень красивая, симметричная, у нее прозрачная архитектура, ну, понятная архитектура. Ее легко учить, она достаточно быстро учится, то есть 1600 снимков, в принципе, оказалось вполне достаточным, чтобы ее обучать. И, собственно, я даже здесь привел еще пару ссылок на другие мои работы, которые я не представляю на этой конференции, вот, но мне было бы приятно, если бы вы посмотрели их, может быть, или задали какие-нибудь вопросы на перерыве. Вот, это тоже по применению той же самой архитектуры UNet, но, может, конечно, с модификациями чуть-чуть. Вот в данном случае это не конволюционная UNet, а обычно полносвязанная, то есть мы ее использовали вообще для другой задачи предсказания химической кинетики, когда у вас есть временной ряд многомерный, и вам нужно предсказывать как бы вот по текущему значению t значение концентрации химических элементов в момент t плюс дельта t. Вот. Эта же самая архитектура очень успешно справилась и получилось достаточно хорошо. Здесь вот на рисунке пример предсказания. Видно, что чуть-чуть они не совпадают, но это самый худший пример. На самом деле они обычно совпадают. Вот. Другая работа, сейчас она еще не опубликована на английском, пока только в русском журнале, связана с фотолитографией в микроэлектронике. Здесь тоже мы применяли архитектуру UNet для задач фотолитографии, когда вы предсказываете по вашему шаблону, то есть у вас есть фотолитографический шаблон, с помощью которого вы хотите создавать некоторые структуры в кристалле, вот, и вы предсказываете то, во что они превратятся после проявления, то есть после нескольких там процессов физико-химических. Вот. UNet архитектура отлично справляется с этой задачей, и вообще как бы изначально, ну, ее можно как бы назвать такой простенькой моделью для перевода картинки в картинку. То есть, когда у вас что-то переходит в такого же типа объект. Вот. Ну, для нашей задачи сегментации рентгеновских изображений мы чуть-чуть ее сократили, то есть сделали всего трехуровневой, то есть чтобы она была компактнее, меньше настраиваемых параметров, чтобы быстрее работала. Вот, в принципе, качество... Нет, мы пробовали разные, и 3, и 5 уровней, да, в принципе, 5 уровней чуть получше оказалось. Вот, но здесь представлено на рисунке 3 уровней. Значит, для тех, кто, может быть, не знает, я вкратце объясню, что здесь нарисовано, то есть что представляет собой это. Ну или давайте на оригинальном рисунке объясню, что здесь происходит. Значит, архитектура UNet — это архитектура, которая в чем-то напоминает вроде как автоэнкодер, то есть конволюционный, деконволюционный автоэнкодер. Вот, но на самом деле она сильно от нее отличается. Отличается она вот этими прямыми стрелочками горизонтальными, которые являются как бы skip connections, ну или прямые соединения, которые соединяют вход с выходом напрямую, передавая информацию без искажений. Вот. А уже вся нейросетевая часть, вот эти вот конволюционные слои, которые синенькими прямоугольниками показаны, это уже все residuals, то есть как бы остатки, потому что основной поток информации, он идет без изменений по этим прямым стрелкам, горизонтальным стрелкам. Вот. Все дополнения, изменения, модификации идут как бы в обход. И на самом деле, чем больше уровней у этой сети, тем, в принципе, может быть, меньше эти уровни и значимы, потому что я уверен, что начиная с некоторого уровня, это, ну, изменения будут незначительны. То есть я это не проверял, но как бы по общим соображениям, скорее всего, это так. Поэтому 3-5 уровней вполне достаточно. Больше, наверное, и не нужно. Вот. Так. И ну, чем хороша эта, значит, нейросеть? Тем, что она может переводить картинку в картинку. Вы на входе подаете некоторые изображения, а на выходе вы ожидаете другое изображение, но того же самого, например, размера. А в данном случае у нас на выходе ожидается вот такая карта аномалий, то есть это бинарная маска, где белым отмечены, ну, единичками отмечены места, в которых человек выделил подозрительные объекты, вот, а черным отмечен фон, там, где вроде ничего страшного не наблюдалось. Вот. Ну, собственно, дальше следовала стандартная архитектура обучения. Мы использовали PyTorch и обучили эту сеть. Вот самые такие первые результаты, как оно получилось у нас. То есть здесь на левом изображении исходная TIFF-картинка, посерединке это маска, которая предсказана нейросетью. Ну а на выходе мы их наложили на предобработанное изображение, чтобы было лучше видно вот эту маску. Вот. И видно, что нейросеть, в принципе, выделяет основные аномалии. Вот. Но часть вещей она отмечает плохо. Вот на укрупненном справа элементе нарисовано там вот в кармане. Указка точно не работает, да? Ну, ладно. А вот там вот в кармане видно, что телефон или что это такое у него, она не выделила только маленький зелененький элемент этого устройства. То есть обращаясь к заказчику, показывая ему, как бы, он нам дает много таких примеров, что вот это вот она выделила, а вот это нет. То есть и с этим тяжело бороться, потому что мы не можем пофиксить это вручную, сказав, ну да, у нас там телефоны не размечаются, или у нас там это... То есть мы не можем сказать конкретно, что в каком случае отмечается нейросеть, а что нет. Вот, это всегда такой тонкий момент с нейросетями, то что нельзя наперед сказать, что будет, и нельзя улучшить результат, даже осознав, что она вот что-то, какие-то вещи не видит. То есть это, чтобы это сделать, нужно существенно что-то менять. Либо менять обучающую выборку, либо архитектуру, либо способ обучения, либо, в общем, какие-то серьезные манипуляции. Вот. Что было дальше нами предложено, как бы разработано? Идея была следующая, точнее даже не идея, а была выявлена следующая проблема. Заказчик сказал, что на картинках отлично распознаются пуговицы, молнии, какие-нибудь кольца, часы, в общем, все металлическое прекрасно распознается, но оно реально очень хорошо видно. Оно очень твердое, непрозрачно для рентгена, и поэтому выглядит как черные области. Вот. А вот какие-то другие там подозрительные вещи плохо распознаются. Вот. Но мы проанализировали это и поняли, что да, действительно так. Оказалось, что просто проблема в самих данных. То есть 1600 снимков, хоть их и много, но в них реально нет тех подозрительных объектов, каких-то полупрозрачных пакетов, каких-то, не знаю, каких-то, в общем, вещей, которые не столь однозначно видимые, то есть их трудно, их просто нет, потому что они нам давали с проходной какого-то завода, где люди обычно нормальные, они проходят туда в халатах без ничего, и как бы самое запрещенное, что могут быть они пронести, это вот действительно какие-то цепочки, какие-нибудь там у них молнии и кнопки на одежде. Вот, и все. То есть они реально добросовестные люди, естественно, никаких важных, опасных объектов в этой выборке нет. То есть, не может заказчик нам дать 1600 снимков с запрещенными объектами, ему нужно поморочиться, чтобы это сделать, попросить множество людей, специально спрятать что-то там, в общем. И мы подумали, что можно, может быть, как-то обойтись без этого и сделать какой-нибудь собственный генератор аномалий. То есть просто программу, которая бы накладывала на эти изображения какие-нибудь полутоновые объекты, похожие на какие-нибудь подозрительные вещи. Вот, ну, в общем, мы сделали такой генератор. Ой, я думал, у нас полный экран, да? Заголовки все закрыты. Ну, в общем, мы сделали генератор аномалий, которые генерируют два типа объектов, да? Ее нельзя спрятать. Ну ладно. Да нет, в заголовках ничего интересного. Пусть будет. Значит, идея генератора в том, чтобы генерировать разные типы объектов. Вот, в качестве таких объектов мы взяли два типа. Это многоугольники, там, треугольники, квадраты, всякие, в общем, многоугольники, которые просто случайно генерируются. И второе, это мы взяли известную всем базу данных Fashionist, где всякие элементы одежды, там, сумочки, юбки, штаны, шорты, обувь. Вот, и они, в общем, их как раз просто брали как некоторые, ну, своеобразные формы, да, то есть не совсем такие прямоугольные, вот, а интересные различные формы, вот, и их накладывали в случайные места, уменьшали, увеличили, да. Вот. Ну, с помощью генератора, скажу честно, о, класс. Ну, удалось действительно получить большую выборку полутоновых каких-то вот таких накладываемых объектов, и это расширило выборку. То есть генератор в данном случае рассматривается просто как аугментация нашей обучающей выборки. То есть мы, ну вот, стандартный способ аугментации — это когда вы там картинку поворачиваете, сдвигаете, обрезаете, чуть-чуть увеличиваете, меняете яркость. Вот. А здесь еще дополнительно накладываете не шум. Шум было бы слишком легко, гауссовый какой-нибудь шум накладывать. Нет, здесь вы именно накладываете какие-то прям такие пятна с некоторыми объектами. Вот. Ну, так, а теперь я переключиться не могу. Вот. Ну, собственно, давайте покажу вам результат. Вот. Ну, здесь вот на левом рисунке оригинально уже предобработанная картинка, чтобы было видно. Посерединке это наш некоторый промежуточный прототип, который без генератора, третий уже с генератором. Вот, видно, что генератор, ну, в общем, на наш взгляд, конечно, оценить численно, к сожалению, результаты мы не смогли, потому что у нас очень маленькая валидационная выборка. То есть мы проверяли результаты на валидационной выборке, которую нам дал заказчик, там около 30 или 40 картинок. Но эти картинки в большом количестве изобилуют всякими подозрительными объектами. Вот здесь вот видите, женщина нарисована, да, на теле которой огромное количество всяких непонятных вещей, там и какие-то колбы, пистолет на запястье, какой-то нож или пуля в ноге, в общем, что попало. Вот. Ну, видно, что на крайнем правом, хотя большинство объектов, в том числе проволока на ноге, там вот на правой ноге, проволока — это тоже очень важный объект, который нас просили размечать. Вот она тоже была размечена. Вот. Но при этом на животе и на груди многие объекты прям выделены красным, то есть это ложное срабатывание во многих случаях. Вообще область груди и живота самая тяжелая, потому что там очень много всего, много внутренних органов, и они всегда разные, по-разному расположены, и часто трудно увидеть среди них что-то полутоновое. Вот так, ну это другой пример. Давайте я сразу перейду вот к этим результатам. Это там время 5 минут. Ну ладно, значит, как сказал наш как обратная связь от нашего заказчика. Вот слева это то, как они видят, то есть как это должно было быть. Вот у человека должна была распознаться бутылка на поясе, телефон в кармане, там еще какие-то небольшие вещи на груди. Вот. Справа это то, что распознала наша нейросеть. Видно, что бутылку она даже не увидела, она ее не заметила, и мы тоже ее не заметили. Потому что справа это предобработка изображения, как мы ее сделали. И мы ее сделали чересчур агрессивной. То есть она настолько подняла яркость изображения, что даже вот такие пластиковые вещи, как бутылка, они просто пропали. Вот. И этот косяк обнаружился очень поздно, на самом деле, через полгода начала работы. То есть только потом мы поняли, что нужно эту агрессивную предобработку улучшать, делать ее менее агрессивной, то есть так, чтобы были видны элементы одежды, были видны элементы вот такие полупрозрачные, и заново переразмечать картинки, потому что если мы на картинках их не выделяли, то значит сеть вообще этому не научится. Вот, и пришлось это все переделывать. Но, то есть здесь, к сожалению, нет, на самом деле, ну да. Вот, но проблема оказалась в том, что даже после того, как мы это переделали, ничего принципиального не поменялось, потому что не было таких изображений, где бы были бутылки на человеке или еще какие-то. То есть таких изображений было буквально единицы из этих 1600 снимков. Вот. И поэтому проблема по-прежнему остается. Проблема с генератором, его нужно улучшать. Вот. Ну, давайте я покажу еще, может, несколько примеров того, что сеть видит, что не видит. Так, эту женщину я уже показывал с пистолетом на запястье. Здесь. Так. Ну, в общем-то, ладно. Если у меня осталось еще парочка минут, хотел рассказать про другие методы, которые мы не использовали. Значит, как я сказал, когда мы увидели эту задачу, мы подумали, что это задача сегментации. И решали ее как задачу сегментации. То есть сводили ее к задаче обучения с учителем и сделали обучающую выборку вручную размеченную. Вот. Но спустя уже там буквально, фактически целый год работы, мы заметили, что есть работы, которые отличаются принципиально по постановке задачи. И, возможно, имеет смысл рассматривать эту задачу не как задачу сегментации, а как задачу детекции выделения аномалий. Anomaly detection — это другая область не только компьютерного зрения. То есть что такое детекция аномалий? Это когда у вас есть какие-то данные, которые в большинстве своих случаев, там, в 99% случаев, они нормальные. Но бывают какие-то выбросы, случайности, какие-то шорохи, какие-то, в общем, вещи аномальные. Вот. И это совершенно другая область. Здесь нельзя ставить задачу как задачу обучения с учителем, потому что обучающих примеров положительных почти нет, то есть 1% из 100. Вот. И для Anomaly Detection вот мне очень понравились пару работ, я их просто здесь приведу, это не наши работы, но мы хотели бы их попробовать в будущем. Вот. Это первое, это патч SVD, то есть SVD это Singular Value чего-то там Decomposition. Вот. И они говорят, что их алгоритм прекрасно работает, выделяя всевозможные аномалии на изображениях. Вот есть такая база данных MVTech AD, она публично доступна. Там вот изображения из разных областей. Вот зубные щетки, какие-то из электроники, фотографии микросхем, ткани, еще что-то. Вот. И везде есть какие-то примеры аномалий. Например, в электронике это когда там ножка распаяна, или в ткани, когда есть какое-нибудь изменение в рисунке. Вот. И они говорят, что у них прекрасно она работает, при том, что учится совершенно без учителя, просто на правильных примерах. То есть принцип работы, значит, этих алгоритмов, если на пальцах он совсем другой. Он состоит в том, что вы создаете некоторую библиотеку правильных примеров. То есть правильных, я имею в виду, без аномалий. Вот. И эта библиотека строится не в исходном пространстве картинок, а в некотором другом пространстве, например, в пространстве репрезентации нейросети, то есть как бы какой-нибудь слой нейросети. Вот. И в этом латентном пространстве вы создаете большую выборку хороших примеров, а потом сравниваете ваши примеры, ну то есть, допустим, какие-нибудь аномальные. Вот. И если в этом латентном пространстве ваши вектора окажутся далеко от тех объектов, которые в вашей библиотеке, значит, можно предположить, ну, как бы поставить вопрос о вероятности того, что это аномальная вещь. Вот. И даже целые конкурсы проводятся. Вот есть сайт Papers with Code, очень популярный, я думаю, многие знают о нем. Вот. И здесь как раз тоже люди соревнуются в задачах детекции аномалий вот на различных датасетах. Вот Шанхай тех датасет, где нужно в толпе людей разглядеть какие-то необычные вещи, например, кто-то там на машине заехал, или вот другой датасет как раз МВТ-КД. В общем, вот PatchCore, еще один алгоритм, да, который здесь занял вообще первое место, он фактически точно так же построен, как PatchSVDD. Очень интересные алгоритмы, хочется попробовать их в будущем, может быть, удастся применить задачи сегментации рентгеновских снимков. Все, спасибо за внимание, я на этом закончу. Да.
Интересно, как вы проводили предобработку, что вот эта бутылка с водой исчезла из данных? В чем она состояла? Почему так получилось? Мне не поняла.
Ну да, да, это, конечно, был наш недосмотр.
В чем состоялось? Что за алгоритм такой интересный?
Мы смотрели разные фильтры. То есть фильтры, связанные с выравниванием гистограммы. То есть если у вас есть вот исходная гистограмма, вот здесь слева внизу оригинальная, да, то есть у вас в основном все пиксели имеют либо оттенки почти белые, либо почти черные. Вот. И мы хотим их как бы чуть-чуть выровнять, более сделать разнообразие повысить. Вот. И начинаем их выравнивать с помощью вот всяких процедур, там, порогового отсечения. Например, все, что выше чего-то, мы просто делаем белым, там, допустим. И так постепенно гистограмма действительно выравнивается, она становится более разнообразной. Ну и это тоже, то есть вот hash-trunk это как раз обрезание по порогу, а equalize hist это эквализация гистограммы. Это прям библиотечная функция из OpenCV. Вот, очень классно работает, особенно еще Equalize Adapt Hist. Вот это адаптивное выравнивание гистограмм, когда ваша картинка бьется на маленькие сектора, там 8 на 8, скажем, и в них делает эквализацию гистограммы. И тогда у вас адаптивность получается как бы в разных местах, они будут по-разному, но в итоге картинка становится совершенно другой, она выглядит потрясающе. То есть вот Equalize Adapt Hist, он же известный как Клахе, вот этот алгоритм. В общем, с помощью них мы делали, но чуть-чуть вот с параметрами мы перестарались и потеряли много. Да.
Больше вопросов, maybe in English.
А нас точно слышат в Zoom?
Они не пишут там ничего? Писем нет? Тогда спасибо большое, раз вопросов нет.
Спасибо.
Я приглашаю следующего доклада. Да?
Hi everybody, my name is Maria Pilgan. I'm so sorry for our presentation in Russian. This is our mistake, I'm so sorry. Мы очень признательны организаторам конференции за возможность поздравить Бориса Григорьевича, выразить ему наше восхищение и благодарность за все, что он сделал в науке о данных. И, конечно, сделает еще. И во всей вот полифонии работ юбиляра для нас особенно важным, конечно, оказался его междисциплинарный подход, который, к удивлению, Борис Григорьевич сформулировал еще в те времена, когда, я думаю, слово междисциплинарный было чем-то неприличным. И вообще, наверное, очень интересно как реагировали коллеги на эти работы, когда в ранних работах еще у Бориса Григорьевича есть буквально интегрированы даже 4, не менее 4 вот, научных парадигм. Конечно, большое значение для нас имеет работа по кластеризации, ну и особенно важно, конечно, ваши работы по интерпретации ваших объемных социологических данных, которые дали нам огромное количество идей, и вот мы продолжаем вас учиться и пытаемся вот тоже строить модели такого анализа. Мы пытаемся интерпретировать данные социальных медиа. Конечно, ландшафт социальных медиа вот в мировом контексте, он достаточно стабилен, в то время как, конечно, цифровая жизнь русскоязычных авторов, особенно в последний год, претерпела колоссальные изменения, но в количественном отношении практически ничего не изменилось. Были только спады 25 февраля и период объявления мобилизации, что естественно. А в принципе цифровые показатели, они как бы такие достаточно стабильные. Поменялось, если количественные данные стабильные, то качественная жизнь, конечно, изменилась кардинально. И, собственно, русскоязычные авторы такой сделали цифровую релокацию, и бенефициаром ее, конечно, стал Telegram. По сути дела, в нашем современном русскоязычном медиапространстве мы имеем только то, что дал нам Павел Валерьевич Дуров. Собственно, вот ВКонтакте и Telegram наша вот цифровая земля. Ну вот одноклассники тоже пытаются сейчас как-то очень активно использовать ситуацию, делают ребрендинг, делают какие-то очень новые модели. Ну и в принципе у них есть какой-то минимальный прирост, но тем не менее все-таки эта платформа находится на периферии цифровой жизни. Цели наших цели исследования, тут вот, собственно, они определены заказчиком, который стройкомплекс Москвы, на основании которого мы делали где-то более 30 проектов, что позволило нам вот говорить о том, что мы создали какую-то модель. Собственно, задача заключалась в том, что, ну, особенно еще в старые добрые времена, еще не такие давние, когда в Москве было более 200, скажем, одновременно строительных площадок, то для стройкомплекса было очень важно, представьте себе, реакция москвичей. То есть, во-первых, где, конечно, очень важна предиктивная аналитика, то есть где могут возникнуть конфликты, и при наличии уже существующей социальной напряженности выявить их причины непосредственно и дать рекомендации, как их быстро нивелировать. Мы эти задачи, мы, собственно, вот на протяжении вот нескольких лет, когда мы этим занимались, все время меняются вот эти наши модели. Вот на сегодняшний день у нас наибольшую эффективность показала некий такой алгоритм, который совмещает 3 вот такие сферы. Нейросетевой семантический анализ, который мы делаем вместе вот с Александром Александровичем Харламовым, вот из тоже МФТИ, это руководитель департамента интеллектуальных систем. Математические модели мы делаем Нелли, и логические процедуры, которые подтверждают или нет результаты, проводят наши коллеги Александр Арсений Николаевич Расходников, это логическое агентство «Столица» и Центр урбанистики «Город» при правительстве Москвы. Собственно, методы используются самые разнообразные, полифоничные, они, в принципе, меняются, но в целом, вот, скажем, и вот эта вот модель, алгоритм, он тоже постоянно изменяется, потому что, во-первых, все время с каждым разом понимаешь, что нужно исправить. Во-вторых, эта среда столь неустойчива и столь быстро меняется, что требует постоянно каких-то вносить в нее какие-то изменения. Ну вот, мне кажется, то, что на сегодняшний день, что вот меня, например, беспокоит больше всего и является большой, скажем, проблемой, это вот выделение искусственных сущностей. То есть еще, скажем, 3 года назад было очевидно, что для анализа вот подобных вещей, когда мы говорим о восприятии, да, и каких-то анализов социологических проблем, что, конечно, очень важно всех искусственных сущностей сначала отделить, да, их выбросить, поскольку они нам как бы мешают вот определить это восприятие живых людей. Но что мы видим сегодня? То есть я, например, в полной растерянности. Во-первых, стоит ли вообще их выбрасывать? Потому что, конечно, после уже GPT-3 появилась какой-то такой несколько растерянность. Но после того, как в ноябре был представлен чат GPT, и мы видим, да, что на нем возможно делать. А завтра уже буквально нам, кажется, грозят представить GPT-4, да, который, если GPT-3 было 175 миллиардных параметров. Тот же GPT-4 обещает, что ли, 100 триллионов больше. То есть очевидно, что эти искусственные сущности, то есть мы с ними, даже если сейчас уже собственные случаи, когда чат GPT, конечно, превосходит биологических акторов, то есть нас с вами. То есть чат GPT-4, то есть от GPT-4 очевидно, что эти искусственные сущности, то есть мы с ними даже соревноваться не сможем. Более того, вот уже анализ показывает, что они во многом определяют качество и движение информационных потоков. И вот что с этим делать, мне кажется, что сейчас вот это такая очень актуальная проблема, но это, я думаю, что это вот уже сейчас, сегодня, завтра, я думаю, что нужно этим непосредственно будет заниматься. Но вот в нашей модели, мне кажется, что самым, таким интересным, это возможность выделения семантических акцентов, которые являются семантических акцентов, причем которые выражены не эксплицитно, а имплицитно. Поскольку в коммуникации и вообще наше вот восприятие, оно, конечно, во многом определяется вот этими имплицитными сферами. И один из, вот помимо семантического ядра и вот этих семантических моделей, это позволяет сделать нам ассоциативный поиск и анализ ассоциативных сетей. То есть, эта практика вообще ассоциативные эксперименты, это такая была достаточно распространенная практика психолингвистики и психологии, которая имеет целый ряд недостатков и совершенно справедливых. Но вот на материале больших данных с помощью нейросетей вот это выделение ассоциаций, конечно, по крайней мере, вроде бы дает возможность интерпретировать имплицитные подтекстовые значения, которые во многом и определяют наши реакции, наши отношения, потому что наши ассоциативные связи мы не можем контролировать и не можем их подделывать, как все остальное. Да, и вот, собственно, поскольку и заказчики, собственно, да и мы с вами, конечно, любим какой-то, помимо вот этих больших моделей, какое-то что-то такое, какие-то цифры, которые нам могут сразу показать, что вот это результат вот каких-то исследований. Мы вот придумали поэтому индекс социального стресса и социального благополучия. У нас, собственно, я не буду на этом останавливаться, это у нас отдельно описано в работах. На его последней работе у нас эта методика достаточно хорошо описана. И, в принципе, он, в общем, работает, по крайней мере, показательно. Шкала вот социального, шкала их, которая одинаковая, в принципе, тоже получается, что приходится двигать там по-разному. И вот, собственно, наши коллеги делают социологические исследования достаточно традиционно, но вот фокус-группы, они, конечно, базируются на тех результатах, которые дает нам семантическая сеть, и, собственно, позволяют делать более такими корректными, проводить саму методику фокус-групп. И что интересно, мы уже вот буквально недавно попробовали результаты фокус-групп тоже проанализировать по этой же нейросетевой модели. То есть то, что никогда не делают. Обычно социологи проводят фокус-группы, как-то их там что-то такое количественно описывают. А вот, собственно, нейросетка позволила вытащить, опять же, семантические нюансы, и вот показалось это тоже очень любопытно. И естественно, что когда все три модели показывают нам, подтверждают один и тот же результат, мы в общем-то, очень довольны и представляем ее и можем говорить о какой-то там валидности результатов. Сегодня мы хотим представить вам очень кратко результаты одного исследования, которые посвящены большой кольцевой линии. Просто, конечно, просто потому, что вот у нас последние данные по этой БКЛ есть, на самом деле ничего в ней там интересного нет. Помимо того, что это, в результатах исследований нет, там никаких страшных конфликтов нет. БКЛ, собственно, она только сейчас запускается, несмотря ни на что. Это один из самых, практически, нет, почему один? Это самый объемный проект стройкомплекса Москвы, поскольку, видите, БКЛ, она такая бирюзовая. Она 96 километров, говорит, нигде вообще нет такой длинной ветки. 31 станция метро на ней будет, 19 переходов на другие линии метро, там 4 перехода на МЦК, там сколько-то, 6 на МЦД. В общем, это очень объемный проект. Мы делали, он, собственно, БК строится с 2011 года, первая ветка запущена была в 2018 году, и мы делали несколько срезов. Собственно, берем мы данные, естественно, все релевантные данные, используем вот эту нейросетевую технологию Сан Саныча, Toral Light, традиционный сетевой анализ, Автомэк, контент-анализ, хотя я вот искренне не понимаю, зачем он нужен, но заказчики его очень любят. И, ну, табло — это просто для визуальной аналитики и рисования красивых картинок. Вот делали, повторяем, мы очень много замеров, потому что большой проект, и естественно, что он как бы очень важен. Но вот сейчас мы хотим показать два датасета, просто последних. Это вот 2020-2021 год и 2022 практически год, что вообще было удивительно, потому что, ну, понятно, что в 2020-2021 году интерес к этому проекту был большой, закономерно, да, но что в 2022 году будет кто-то интересоваться и генерировать контент про БКЛ, для меня, например, было, я думаю, что вообще там не будет этого ничего. Тем не менее, посмотрите, если учесть, что вот первый датасет — это 9 месяцев, а второй — 12, то есть, ну, практически сопоставимо по месяцам, да, объем генерированного контента, что вообще, конечно, удивительно. Ну, первые характеристики касаются, собственно, естественно, цифровых источников. И вот первый датасет отражает достаточно такую типичную картину для того времени, еще года назад. Это микроблоги, мессенджеры и социальные сети, видео в 4 месте. Но вот, конечно, типы источников по охвату показывают, уже сами дают, конечно, очень любопытный результат. Вот этот твиттер, который выходит в лидеры, коллеги, конечно, не говорит о том, что Твиттер у нас когда-то был первый там по популярности цифровой платформы. Никогда этого не было в русскоязычной среде. То есть это единственное, живых людей там было очень мало. Это, как правило, билингвы, которые живут, скажем, в англоязычной среде, где Твиттер, ну, скажем, для американских, да, или британских пользователей, Твиттер — это вообще основная среда обитания, и русскоязычные вот билингвы, они также переходят и в Твиттер. В принципе, вот эта картинка показывает только о том, какие колоссальные бюджеты были потрачены на информационное сопровождение. Вот в Твиттере были в основном только вот эти, знаете, бюджеты вот этих пиарщиков и журналистов, которые, значит, гонялись там туда-сюда, ну, бюджеты огромные. Это вот, собственно, просто называется, по-моему, это совершенно чудовищная ситуация. Ну и обратите внимание, что уже тогда Telegram был на первом месте, ВКонтакте и YouTube. Очень необычное распределение для типов источников. Повторяю, это первый датасет. Но вот цифровые среды, конечно, на них, безусловно, следует обращать внимание, и невозможно не обращать внимания. Но, коллеги, опять же, мы знаем огромное количество механизмов на сегодняшний день, которые позволяют вот, ну, искусственным образом создавать вот эти цифровые следы, которые, ну, делают совершенно не актуальную реальную картину цифровой оценки пользователей. То есть, опять же, большинство из них, то есть, достаточно очень дешево, очень просто нагнать количество там лайков, дизлайков и прочее. Поэтому этот показатель тоже такой, к нему относимся с большим таким осторожностью. Ну, распределение цифровых следов тоже традиционное, конечно, показывает наибольшую активность ВКонтакте, который у нас понятный, любимый, удобный. Динамика вот общего числа сообщений, числа уникальных сообщений, количество просмотров и количество активности акторов вот, по первому датасету дают одну и ту же картину. Практически нейтральное поле, только два всплеска. Они относятся к 26 марту и к 6 апрелю. И, вы знаете, тоже совершенно чудесная ситуация. То есть в те времена недалекие вот эти всплески связаны были с тем, что первый всплеск это с тем же было в активном Константине и вообще в сетях обсуждений, как назвать новую станцию. То есть вот еще год назад москвичей очень сильно волновало, как назвать новую станцию. И это, значит, эти были вот с этим связаны всплески. А второй всплеск с открытием народного ополчения. Там с этой станцией просто было связано много проблем. Второй датасет, который отражает, собственно, вот этот наш 22 год, традиционный, он показывает, конечно, тут опять же социальные сети уже выделяются, поскольку развитие Телеграма, то здесь уже следует, конечно, разделять каналы и чаты мессенджеров, и прежде всего Телеграма. Ну вот видео и блоги, которые выходят, соответственно, на 3-е и 4-е место. Среди источников вот это уже ситуация говорит о том, что, конечно, бюджеты на информационное сопровождение уже практически не тратились. И здесь вот реальная картина цифрового поведения русскоязычных пользователей ВКонтакте, Телеграм и YouTube. Причем обратите внимание, что Инстаграм и Фейсбук тоже как бы привет Роскомнадзору, да, вполне себе живы, хотя, конечно, резко похудели. В данном случае вот эта же динамика упоминаний, динамика активности, динамика вовлеченности и активности аудитории показывает совершенно другую картину. Конечно, в 2020 году пользователи волновали совершенно другие проблемы. Единственное, что вызывало какую-то резкую реакцию, это сообщение, информационное сообщение о сроках. И вот этот пик, видите, активности аудитории связан с тем, что было сообщение мэра о том, что завершили наконец ПКЛ, и, значит, он вот будет, наконец-то его запустит в ход. Вот, ну, по гендерному распределению, как следовало ожидать, конечно, мужчины более активны при обсуждении таких проблем, люди 55 лет и старше. Но вот, что меня потрясло, совершенно геолокация акторов. То есть 22 год, да, люди. Ну, вообще надо сказать, что удивительно, что все московские вот эти проекты, они дают какую-то совершенно безумную геолокацию, что даже там какие-то появляются названия стран, которых я даже и не знала. Но здесь, вот представьте, да, себе какой-то остров Кука, сидит человек на острове Кука и генерирует контакт по БКЛ. При том, при всем, что, конечно, геолокация в аналитике вызывает много, конечно, есть у них очень много проблем, и, конечно, с ней нужно относиться, понятно, что там не все точно, но, тем не менее, общая картина вполне себе. Ну и по странам геолокации, конечно, вот очень нравится сочетание, конечно, Зеленограда и Нью-Йорка. Ну, это по количеству, да, по количеству активности к этой проблеме. Вот тональность, сентимент-анализ, безусловно, и кластеризация по тональности, это, конечно, очень важный такой момент первичный, который, ну, без которого нельзя обойтись. И вот он дает, ну, как в первом-втором датасете, дает показания большей тональности по нейтральному контенту. И рост вот динамики, рост динамики сообщений к 2020-2021 году, поскольку именно в 2021 году стала активная фаза строительства, поэтому, собственно, вот этот первый датасет вот с этим связан, когда была активная фаза строительства, и строительство вышло вот на поверхность, то есть москвичи непосредственно с этим столкнулись. Но, тем не менее, все показывает, собственно, видите, преимущество нейтральных сообщений. Ну, вот топ источников с позитивной тональностью ВКонтакте, Мосро, Телеграм. Надо сказать, что это, конечно, в основном нейтральная и позитивная тональность, это ангажированные медийные ресурсы. И вообще, конечно, совершенно потрясающе, каким образом вот наши журналисты и пиарщики, которые вот какие-то безумные осваивают бюджеты на это сопровождение, они умудряются добиться прямо противоположных целей тому, за что им платят, и, собственно, тех целей, которые они ставят. Чем больше позитивного нейтрального контента они генерируют, тем больше вызывает отторжение у аудитории. И реальные реакции пользователей вот это, собственно, показывают. Ну, второй датасет также показывает преимущество нейтрального контента, да, но и тональность разных типов в соответствии с разными аудиториями. Тем не менее, видите, показывает, что в комментариях негативных сообщений больше. И это уже такой очень важный звонок. Очевидно, что сообщественно, что вот эмоциональная реакция разгонялась в большей степени в сообществах. То есть как в офлайн-среде, так и в онлайн-среде. Эмоции, вот вирусное распространение эмоций, конечно, наиболее эффективно в толпе. То есть толпа в цифровом пространстве – это сообщество. Но вот это, я уже говорила, что вот очень вот наши проекты и вообще опыт показывает, что отношение к сентимент-анализу, к результатам тональности, оно очень должно быть осторожным, потому что вот распределение по тональности, оно далеко не всегда свидетельствует о реальном положении вещей, если мы хотим говорить о каких-то истинных реакциях, о настоящих реакциях пользователей. В то время как агрессия, анализ агрессии, показывает это вот очень четко. И даже минимальные показатели агрессии вот выявляют истинные отношения, вот истинные проблемы, которые будут присутствовать в сюжете. Ведь, собственно, здесь вот мессенджеры, причем чаты мессенджеров и соцсети показывают нам тип агрессии. И главное, вот здесь вот что-то на комментарии, которые показывают вот достаточно большие проблемы. Это сводная таблица. Видите, я все это закрасила специально в пастельные тона, потому что так страшно, чтобы самой не испугаться. Поскольку агрессия, особенно в русскоязычном вот, генерируемом контексте, это всегда просто чудовищные данные. Ой, так, поскольку у меня уже нет времени, у нас очень много всего, давайте, собственно, тональность в разных, то есть тональность в разных перейду, собственно, к основному, вот ключевые семантические акценты негативные. Позволили выделить прежде всего претензии к проектировщикам, то есть по первому датасету и по второму. Это претензии при том, что не учитываются, жители считают, что были нарушены градостроительные какие-то закономерности, не учтены их нужды, совершенно возмущение против отсутствия диалога с властями и качества проведения публичных чтений. Публичное чтение – это вообще особый разговор. Очень много критиковали расположение новых станций, которые, казалось бы, непродуманных. Собственно, снижение уровня жизни из-за шума. То жителям обещали застраховать их жилье, что не везде было сделано. Расположение выходов, перенос земных переходов, повышенный уровень шума, работы в ночное время, тротуары, которые переносятся под окнами домов, опасность техногенных катастроф, ухудшение транспортной ситуации, конечно, разрушение зеленой зоны, перемещение, собственно, одна из важных претензий, то, что, естественно, жители Старой Москвы, то, что вот эти новые ветки, которые касаются только жителей Новой Москвы, для них только вредны. Собственно, это еще Лужков, кстати говоря, завершал строение линий сознательно только в рамках Старой Москвы. И сознательно продлевал их далее. И естественно, потому что это совершенно закономерно вызывает негативные реакции жителей Старой Москвы. Усложнение ситуации транспортировок, и многое другое. И, конечно, эти конфликты накладываются на старые конфликты, связанные вот тут, например, со строительством линии сульти-новаторов до Севастопольского проекта, проспекта. А, скажем, во втором датасете они накладываются на проблемы, связанные с инновацией по-разному. Во втором датасете тоже было достаточно много повторяющихся, таких же, собственно, повторяющихся, и, конечно, было намного меньше этих акцентов, но появились, например, новые. Кстати говоря, вы знаете, удивительно, скажем, такое сожаление о том, что вот качество строительства, которое очень плохое, а в советские времена, оказывается, оно было замечательное, не было никаких протечек. Вот. Неудачный, да, и вот появился тоже новое, что БКЛ – это устаревший проект, который потерял свою актуальность. Несколько других акцентов, просто за неимением времени я показываю, собственно, рейтинг социальной напряженности, вот позволил выделить Воронцовскую станцию метро, которые возможны потенциальные конфликты. Очень низкий уровень, но все-таки он существует. И вот, собственно, еще Каховская, Дюзина и Новаторская, которые тоже выделили среди этих 31. И вот индекс социальной напряженности, индексы показали, что во-первых, индекс, конечно, снизился в 2022 году, но, в принципе, он показал достаточно низкие значения для социального стресса и для социального благополучия. И, разумеется, что в 2022 году эти данные вообще уменьшились в 2 раза, потому что очевидно, что, несмотря на активность пользователей, проблемы были совершенно другие у людей. Эти данные мы проверили на 4 математических моделях, которые тоже у нас представлены, и вот агрессионные модели, модель тренда ряда, первого ряда, математические модели с использованием АДО, у нас это все в статье написано подробно, модель основана на стохастических дифференциальных уравнениях с использованием CNN и сравнительный анализ. Данные, собственно, результаты математического анализа, математические модели подтвердили данные нейросетевого анализа, и дальше были проведены логические фокус-группы, которые также позволили уточнить и подтвердить результаты. В данном случае вот эта идентичность результатов по 3 моделям дала нам, скажем, уверенность в том, что мы сделали правильные выводы, которые связаны с тем, что анализ спокойное восприятие москвичей. Особые, конечно, проблемы связаны с тем, когда закончится строительство, потому что очень долго длится, с ним много проблем. И вот единственный потенциальный конфликт связан со станцией Воронцовская. а также сделать, вот, позволила сделать ряд рекомендаций для того, чтобы нивелировать существующее социальное напряжение, которое все равно присутствует и которое нужно как-то решать. Ну, я думаю, что я уложилась. Спасибо.
Ну, давайте начнем с Бориса Григорьевича.
Очень интересный доклад. Я вот хотел узнать, и там, мне кажется, что есть почва вот для применения моих методов анализа таблиц сопряженности. Вот у меня такой конкретный вопрос. Значит, вот недовольство жителей каким-то переходом. А фиксируется, что какие-то жители, наоборот, довольны этим переходом. Какое-то сопоставление возможно делать там, но какие-то активные люди, нет, мы не хотим здесь переходить, хотим там, а 90% наоборот хотят. Вот какие-то такие данные тоже есть или нет?
Да, и мы пытаемся, конечно, их нужно пытаться вытащить, естественно, что мы делаем, то есть по, скажем, по 3 классам, значит, позитивный, негативный и нейтральный кластер. Конечно, позитивный, если кто-то говорит, конечно, мы это делаем. И главное по агрессии, тоже где отсутствие наличия агрессии. Здесь главная проблема в том, что когда люди довольны, они... А когда недовольны даже каким-то одним. Вы знаете, вот был, кстати, совершенно, ну, меня тоже потрясла ситуация с метро вот в Фистех. Вот когда вот метро, вот линия в Фистех. Например, это же еще во времена, она, знаете, тоже очень давно затевалась, и это должна была быть ветка, когда на Дмитровке, там рядом с центром Федорова, когда еще был же Федоров, он даже туда собирался ее тянуть, и она уже была нарисована, и тут, значит, Федоров умирает, и все это замирает в 20 лет. То есть люди покупали квартиры, думали, что там метро будет, люди, значит, в нетерпении. И через 20 лет, когда тянут это метро, и нам дали этот проект, и потом я знаю хорошо этот район, я была уверена, что вообще все будет спокойно, вообще все будут счастливы там и в чепчики бросать в воздух. Куда там? Там были, значит, поскольку Дмитровка достаточно широкая, но там кусок был по наземное метро. И вот люди, которые жили прямо вдоль Дмитровки, стали писать вот негативные отзывы. Их было очень немного, а позитивные, естественно, это были довольны, они как, 20 лет ждали, дождались, они сидят довольны, ждут, когда откроют метро. Но, вот надо сказать, что тоже меня удивило, но это, в принципе, типичная реакция для Собянина. Он после вот этих вот исследований, после этих данных, он пошел на резкое дорожание проекта и сделали его подземным. Ну, вообще, вот это, конечно, да, этих людей, это процент по отношению. Спасибо. Мы будем, конечно, вы понимаете, что мы применяем же только то, что мы понимаем в ваших работах. Не так просто разобраться. То есть мы, конечно, были бы счастливы какую-нибудь модель использовать.
Профессор Воронцов.
Да, нет.
Вот такой большой объем данных, и вы пишете, что это все про БКЛ. Ну, понятно, что вы глазами это не проверили. А как вы вообще понимаете, что в этих данных нет грязи или мало грязи, какой-то процент там маленький? Были ли какие-то эксперименты и специальные усилия? Вообще, как отфильтровать данные, чтобы получить все про БКЛ? Это какой-то список ключевых слов, словарь или что?
Значит, со сборщиком, то есть у нас сначала было очень много проблем с этим, и, то есть, в принципе, мы использовали очень много грязи, то есть много разных вообще примеров. Это было еще несколько лет назад, когда мы только начинали делать эти проекты. И, в принципе, потом совершенно на сегодняшний день проблем практически нет, потому что, как показали вот сравнение результаты, Brand Analytics. У нас же заказчик-то толстый, упитанный, пожалуйста, тебе. Они дорогие, конечно, данные, они самые лидеры на рынке, поэтому они цены там безумные устанавливают. Но наш заказчик, вот берем, собственно говоря, у них данные прекрасные. Ну вот поэтому там, конечно, приходится их чистить, но уже в ходе работы это уже не проблема. Вот когда, например, мы начинали работать, когда вдруг там по каким-то причинам пришлось перейти на Крипер, на другие вот сборщики, это была катастрофа. То есть тоже сразу ясно, что это... Ну это вот тоже путем, то есть это можно как делать, но это совершенно... Очень Brand Analytics наша... Все. Поэтому проблема решает. Oh, I'm so sorry. Correct.
Thank you very much.
Thank you.
Если мы сделаем произвольную постобработку вот этой матрицы, вопрос, соответствует ли это какому-нибудь регуляризатору? Ответ – да. И вот он написан. То есть мы можем просто какой-то эвристический алгоритм применить вот к этой матрице, рассматривая последовательность векторов слов в тексте просто как пучок временных рядов. что-то с ними сглазить, разредить, еще что-то сделать. И что бы мы ни делали, это будет регуляризатор. Ну вот, собственно, да, частный случай здесь рассмотрен, сейчас я это не буду. Да, и оказалось, что такой регуляризатор, он одновременно улучшает несколько характеристик тематической модели. Разреженность, различность тем, когерентность тем и так далее. Теперь немножечко про приложение тематического моделирования, их всякое много разных. Вот, но поскольку мы занимаемся разными проектами в области Digital Humanities, да, цифровых гуманитарных исследований, то там к тематической модели предъявляется сразу совокупность требований. И вот все то, что мы умеем записывать как регуляризаторы, это надо применять вместе. То есть тематическая модель, она должна быть интерпретируемой, иерархической, темпоральной, то есть время учитывать, если это соцсети или научные публикации, мультимодальной там, и так далее. То есть все и сразу мы хотим. Вот регуляризаторов много всяких разных, я их тут в качестве пиктограммок изобразил, чтобы можно было так глазом сразу понимать, что про что, и вместо формул потом писать вот на языке пиктограммок, что хотим. И вся вот эта вот техника, она у нас реализована в проекте, который называется Big ARTM. Да, забыл сказать, главное, ARTM — это аддитивная регуляризация тематических моделей. Приставка Big подсказывает, что большие данные мы умеем обрабатывать. И самое главное, в сравнении с байесовским подходом, в чем преимущество? В том, что унификация появляется. В том, что можно этот алгоритм реализовать один раз в промышленном коде, а потом регуляризаторы менять как перчатки и даже комбинировать их с помощью суммирования взвешенного. А вот в байесовском тематическом моделировании каждую модель надо вывести заново все формулы, потом заново реализовать в коде, потом отладить. Ну и поэтому получается, что большинство тематических моделей, а их сотни в литературе, это вот модели на одну статью. И каких-то коммерческих приложений индустриальных они, как правило, не находят, кроме LDA, которые все знают уже 20 лет. Вот, собственно, BigARTM, наш open-source продукт. С 2014 года мы его развиваем, есть документация на сайте и так далее. Хочется немножечко про приложение. Да, это вот эксперимент, который показывает, что он где-то в 10-20 раз быстрее ближайших конкурентов. Это GenSim и WPL-Wabbit. Просто эффективная распараллеленная реализация сделана на ядрах, без графических карт, кстати. Вот. И дальше у меня примеры примерно 10-12 разных приложений, но по времени я уже не успеваю об этом рассказать. Главная суть, что вы всегда увидите в середине картинки вот такой вот мешок регуляризаторов. То есть это те ограничения, которые мы накладываем на модель, чтобы она удовлетворяла тем свойствам, которые мы хотим потребовать от тематической модели. Занимаемся ли мы разведочным поиском? Вот тут парочка исследований была недавно, кандидатскую диссертацию Анастасия Янина защитила. Или занимаемся классификацией научных статей по рубрикаторам. Или мы занимаемся поиском в социальных сетях дискурса, который относится к обсуждению межнациональных отношений. Или делаем, что еще, ну много тут чего делаем, вот сценарный анализ записей колл-центра. Так, это мне уже напоминает, что у меня закончилось время. А вот я не знаю, как теперь снять это напоминание. Что ж такое-то? Вот, я сейчас уже быстренько заканчиваю. Да, Topic Detection and Tracking – это обработка, да, новостных потоков. Выявление поляризованных мнений в политических новостях. Отдельная задача, очень интересная, рассказал бы, но времени нет. Вот, но главная мысль, да, что все вот эти вот задачи разнообразные из области текстовой аналитики, они решаются с помощью вот этого вот самого инструмента аддитивной регуляризации, где мы просто говорим, какие мы хотим потребовать вещи от этой модели, и делаем из этих требований линейную комбинацию. Банковские транзакционные данные можно обрабатывать так же, как и тексты, ну и так далее. Значит, резюмируя, вот я утверждаю, что если бы вот лемма, с которой я начал, она кажется совершенно классической, вроде бы она в учебниках должна была быть, но специалисты по оптимизации говорят, что они такой леммы не знают, такой теоремы, почему-то. Если бы вообще сообщество знало об этом результате, то я думаю, что вот эти 20 лет развития вероятностно-математического моделирования, они бы прошли бы совсем по-другому, не под знаком байесовского вывода, а под знаком вот такой вот регуляризации, потому что она радикально упрощает математику. Сейчас тематическое моделирование живет нейросетевыми моделями, и вот здесь возникает еще одна заманчивая возможность. Эту же лемму можно использовать в тех случаях, когда в вашей нейронной сети есть векторные параметры, которые по какой-то причине вы хотите сделать неотрицательными нормированными. Такие случаи бывают. И уж точно, если этот инструмент встроить в, например, PyTorch, то с его помощью можно строить любые вероятностные тематические модели, эффективно распараллеливая это на графических картах. Этого мы пока еще не делали, делюсь идеей, над этим мои студенты сейчас работают. Ну вот, собственно, да. И все на этом. Спасибо за внимание. Готов ответить на вопросы, если есть. Так, сейчас.
У меня вопрос. А Борис Теодорович что-то знает про эту лемму? Поляк?
По-моему, я когда-то выступал у них, но тогда, по-моему, я не рассказывал вот так.
Я все понял.
Вот 8 лет занимался тематическими моделями, понять, что все это вытекает из одной единственной леммы, удалось лишь 2 года назад. Такое бывает. Ну вот, собственно, она. Любая непрерывно дифференцируемая функция f, которая задана на наборе нормированных неотрицательных векторов, может быть оптимизирована с помощью вот такого итерационного процесса. Ну, потому что вообще классическая регуляризация тихоновская — это добавление чего-то. Так удобно. Но, наверное, можно было бы там и умножить, но задача бы усложнилась. Нам же продифференцировать надо. Дифференцирование — операция аддитивная. Значит, удобно, взвешенную сумму. А потом это же мультикритериальная оптимизация. А в многокритериальной оптимизации скаляризация критериев — это один из самых простейших основных приемов. То есть, собственно, все, чем мы занимаемся, это многокритериальная оптимизация путем складывания критериев во взвешенную сумму.
А есть теорема о том, что как бы к этому можно все свести?
Как бы это по построению мы так делаем.
Мы с Полищуком в свое время доказали, что этот путь не универсальный.
Конечно.
Полищук — это кто? Леня, да. Мы, значит, здесь, но я все равно все пользуются вот этими аддитивными, потому что они интерпретируют, потому что они понятны. Лиги вот эти, все табличные лиги на них основаны. Я потом отдельно с вами расскажу. Универсальный способ — это путем комплектов. Весов. Ну, я не буду, в общем, вот это вообще-то более сложная техника, и она не линейная. Мы занимались у нас, он же диссертацию написал по многокритериалу. Извините.
Очень интересно.
Вы гарантируете только локальный квант?
Там гарантирована просто сходимость в слабом смысле. И на самом деле в EM-алгоритме, в теории EM-алгоритма тоже довольно слабые условия сходимости.
Коллеги, я предлагаю, сейчас будет перерыв после проекта. У нас будет кофе-брейк. Я надеюсь, вы нам не откажете.
Конечно, с удовольствием.
Я извиняюсь, но потому что он торопится. Он меня очень просил ровно в 8 утра, там, по его времени. Давайте, можно объявить, да?
Да. Спасибо.
Вам спасибо. Давайте похлопаем, а то что-то мы как-то сидим.
Okay, well, I'm happy to join you all today. I'm sorry I can't be there in person for a special occasion. But let me start by wishing a special happy birthday to my friend Boris. I hope this day will be only the beginning of another long and fruitful many years for you. And thank you for all of the collaborations and your special friendship. So I'd like to talk today about the spread and control of disease. And of course, the current pandemic is just the latest and the most, maybe the most devastating example of newly emerging diseases that threaten not only our lives, but our economy and our social systems. It's not the first one, and it won't be the last one. And of course, we've had Ebola, we've had Zika, we had SARS, and who knows what is next. I'm sorry for some of these pictures that are a little bit graphic. The study of mathematical models of infectious diseases goes way back. Goes back to Daniel Bernoulli's study of smallpox in 1760. During the pandemic, we have learned that a tremendous amount of data analysis is very important, and that's one of the themes of this meeting. A tremendous amount of modern computer methods and mathematical modeling and simulation is very important. Optimization is very important. That's another theme of this meeting. We've also learned to be, over the many years we've studied diseases, to be concerned about deliberate introduction of diseases. And then I'll come back to that point in a little while. The diseases are spread through social networks. Contact tracing is an important part of any strategy that you would use to combat them. So I'm going to illustrate contact tracing and disease spread through social networks by looking at some very simple models. I call them toy models because they're not large, sophisticated models, but they do lead to interesting graph theoretical problems. And I chose them in part to reflect some of the key themes of Boris Mirkin's work and the themes of this conference, data analysis, optimization, and their applications. So again, the emphasis is on the graph theory. I'll mention the applications, and hopefully we gain interesting insight even from simple models. So basically, my model will be in a graph with vertices and edges. The vertices are people, the edges means they have a contact, and the vertices are going to be in two states. They're either going to be susceptible, which are green, or they will be infected, which are red. And we'll look at this every discrete time. And then we'll ask, how does disease spread? Now, of course, this is really oversimplified. There can be many other states besides susceptible and infected. We can have an exposed state, we can have a recovered state, et cetera, et cetera. Now, I'm going to study something that is labeled an irreversible K-threshold process. And in this process, you get infected if at least K of your neighbors are infected. So you move your state from green to red if the time before there are enough red ones. Special case is K equals 1, a highly infective disease that if any of your neighbors is infected, you get infected. And we'll come back to that. So here's a simple example. At time t equals 0, there are 2 infected people. And K equals 2 means if you have 2 infected neighbors, you will get infected. So the next time, this is how we started. The next time, this vertex and this vertex get infected because 2 of their neighbors are infected. But after that, the disease doesn't spread because there is nobody else left who is susceptible but has 2 infected neighbors. A very simple example. Here's a slightly more interesting one with K equals 3. And here we start with 4 infected people, but at the next time, A becomes infected because it has 3 infected neighbors, and at the next time, G is going to be infected, and then everyone is. So this is a very simple model. We could change it to get infected only with a certain probability. You could have the K different for different vertices. You could be automatically cured after a while, or you could vaccinate people. And I'll come back to vaccination in a little while. So I'm going to look at the attacker's problem. This is the bioterrorist. Given a graph, what subsets of the vertices should we plant the disease with so ultimately as many people as possible will get infected? That really arises also in economics. We want to place a new product with a few people to guarantee that it saturates the market and everyone else gets it eventually. And of course, you could look at this from a defender's point of view. What subsets of the vertices should you defend to guarantee as few people as possible will be infected? So we call this an irreversible K conversion set if it's a set of vertices that can force one of these processes to the situation where every state is infected. So what's an irreversible two conversion set for this graph? If you infect X1 and X3 at the beginning, then at the next step, if K is 2, if 2 of your neighbors are infected, at the next step, we have X2 infected. And at the next step, we would have X5 and X4 infected. And at the next step, we'd have X6 infected, and then everyone is infected. So X1 and X3 forms an irreversible two conversion set. So let's ask how difficult it is to find whether there is an irreversible K conversion set of size at most P. How difficult is this problem? Well, it turns out that that's an NP complete problem, at least when K is bigger than 2. And more recently, it was shown that even for K equals 2, and even for graphs where the maximum number of neighbors of a vertex is 4, even then the problem is NP complete. So this problem has been studied for many special graphs. And let me just give you a few examples in the short time I have. I don't have time for very many. So a graph is R regular if every vertex has the degree R, and a set of vertices is independent if there are no edges in it. So an early result is that if you have an R regular graph that's connected, so every vertex can reach every other one, D, a subset of the vertices, is an irreversible R conversion set if and only if the complement is independent. So there are no edges outside of among vertices in D. And notice that it's the same R, so that's a very special situation where we're looking at an R conversion process in a graph where every vertex has degree R. Now, of course, this has been generalized significantly, and there are numerous results about R conversion with every vertex having degree R+1, and so on and so forth. This problem has also been studied for rectangular grid graphs. G of Mn has M rows and N columns. This is G of 3, 4 that I'm showing here. This problem has also been studied for toroidal graphs where T of Mn, where we join each top vertex to each bottom one in the same column, and each first vertex to each last one in each row. Such graphs are easier to deal with than the ordinary rectangular grids because every vertex has the same degree. So here is T of 3, 4. And here are a few results. So if you have a toroidal grid, an M by N toroidal grid, you can calculate exactly the size of the smallest irreversible 4 conversion set. So again, a special case because we're looking at, you have to have 4 neighbors that are infected in order to get infected. And 4 is also the number of neighbors every vertex has. So I'll skip the proof, but it's basically just looking at what it means to be independent in a toroidal graph. We have exact results about the smallest irreversible K conversion set in the ordinary grids as well, at least when K equals 4. We know the size of the smallest irreversible K conversion set. I'll use the notation C sub K of G. We also know it when K equals 2, but we only have bounds when K equals 3. So there's been a flurry of papers in this field ever since the early papers were written, but there are still a lot of open questions. And here we only have bounds on the smallest 3 conversion set for ordinary rectangular grid. Now, other people have worked on slightly different process where the defender can start vaccinating people to protect against the spread of disease. So let's suppose that we can vaccinate V people every time period. And let's suppose that, as a simple case, the attacker can only infect people at the beginning. And then let's build an irreversible K threshold model and ask what vaccination strategies are effective. Sometimes in the literature, this has been called the firefighter problem. So here we think of the fire being set at the beginning as opposed to people being infected. And then we place firefighters rather than vaccinations. Now, you could look at this problem where the vaccinator and infector alternate turns and have V vaccinations per time period and I doses of the disease per time period. I won't look into that version here. So I want to give you some results on the firefighter problem. So here's the simplest case. K equals 1 means that one person, that you are infected if you have one infected neighbor, or in other words, the fire is spreading if you have one fire next to you. And you get to have 3 vaccinations every time period. So here I have a fire starting, and now you can vaccinate 3 people, and it's a good idea to vaccinate 3 people near the fire, or put 3 firefighters there. And now I'm going to let the fire spread, and it spreads to every neighbor because we're talking about K equals 1. So as long as one neighbor is unprotected, it gets infected. Now we have 3 more firefighters. We can put them down. And now there's 1 more fire that is not defended. So it spreads. And now we once again put down 3 firefighters, and now we have fire spreading 1 more time. And then we've put down 3 firefighters, and we have controlled the fire or controlled the disease. So this problem has been studied rather extensively. And some of the questions that we might ask are, can the fire be contained? How many time steps are required before the fire is contained? How many firefighters do you need per time step? How many vertices will be saved? And does it matter where the fire breaks out? And does it matter if the fire starts at more than one place? And so on and so forth. So again, I only have time for a few results here. Let's take a look at infinite grids. So an infinite grid in the one-dimensional case is just a straight line, and the fire starts at one vertex, and you obviously need several firefighters to put this out, or it keeps spreading. If you have a two-dimensional grid, it's impossible to contain the fire with just one firefighter per time step. But if you have 2 firefighters each time step, you can contain the fire. And here I'm just going to let this play out. The fire spreads. Remember, if there's any unprotected neighbor, the firefighters, you have two of them, you can put them down. The fire is spreading. And of course, you can think also, instead of fire, you think of a disease spreading and your vaccinations. And when you're done, this took 8 time steps and 18 vertices were burned for this particular attempt to control the fire. How optimal is this particular strategy that I just had on this slide? Can you save more vertices? And can you control the fire in less than 8 time steps? And the answer is no. You cannot do better than 18, and you cannot do better than 8. So this is actually optimal. Now, if you go to dimension 3 or higher, and let's talk first about an R regular graph. So every vertex has the same degree R. Then R minus 1 firefighters per time step are always sufficient to contain a fire outbreak. So if you start with a fire and you use R minus 1 firefighters, the fire will spread to the one unprotected neighbor. But then we can put R minus 1 more firefighters here, and then the fire is protected in 2 steps. So that's easy. In an infinite d-dimensional grid, every vertex has degree 2d. And so this is a 2d regular graph. And so 2d minus 1 firefighters per time step are sufficient to contain any outbreak that starts at 1 vertex. 2d minus 2 is not enough. And so we know optimally 2d minus 1 is the best that we can do. And we also know you can contain in 2 time steps, so that's optimal. A little bit more, if d equals 2, 2 firefighters per time step are sufficient to contain an outbreak, even if you have an outbreak at more than 1 vertex. But for any d at least 3, no matter what the integer f is, that fixed number of firefighters f per time step is not sufficient to contain all outbreaks in LD. In other words, no matter what integer f you give me, there's an outbreak so that f firefighters per time step cannot control it, which is interesting. If you always need possibly large amounts of vaccine to control a disease. So if you allow more than 1 firefighter per time step, and that can be different depending on the time. There are some known results when the function f of t, the number of firefighters available at time t, is periodic with period pf. In that case, if you calculate the average number of firefighters available per time period, then in a 2-dimensional grid, and a periodic number of firefighters per time period, and if the average number of firefighters available is more than 1.5, then no matter how many vertices an outbreak starts at, it can be contained at a finite number of vertices. So there are many such results in the literature and many open questions. Here's one about the situation in which f of t over t to the d minus 2 goes to 0. Then the conjecture is that there's a fire that can't be contained with f of t firefighters at time t. So other work has been done on infinite triangular grids and infinite hexagonal grids. One more thing I think I'll have time to talk about is the maximum number of vertices that can be saved in G if a fire starts at V in finite grids. So here, this happens to be an n by n finite grid. And the theorem is that the maximum number of vertices that can be saved in n by n grid that starts at the vertex AB, to be row A and column B, is at least this number. So it doesn't matter what the details are, but we have a lower bound here. We don't have an exact result. So here's an example to show how that result is. A fire started here, and now using several fighters at each step. And we are seeing that as this plays out, we have obtained the desired result. And again, and here's with a fire that started over here. Here we have an exact result. So the main point I would like to make here is that we have bounds for the maximum number of vertices that can be saved if a fire starts at a vertex V in a finite grid. I showed you what the bound is for an n by n grid. This is the two-dimensional grid. There are results about three-dimensional grids and so on and so forth, but there are many open questions here. I've only begun to scratch the surface in this type of work, and there are many oversimplifications in the models that I've shown. So you might ask, what if you stay infected or stay on fire only a certain number of days, and then you go back to the susceptible state or to the unburned state? What if you're not necessarily infected for the first few days that you're sick? Or what if your threshold changes depending on how long you've been uninfected? So the longer you've been uninfected, maybe the better chance you have of becoming infected. So I can also consider a process in which you stay in the infected state for a certain amount of time, and then you go back to being uninfected. Or you stay burning for a certain amount of time, and then you go back to being unburned. It's a little bit less realistic. I want to also consider the possibility of vaccinating with a different strategy, namely vaccinate everybody who has been uninfected for a certain amount of time, or until a certain number of your neighbors are infected. So you can experiment with a wide variety of assumptions. We can also look at probabilistic assumptions. So what if you only get infected with a certain probability if you meet infected people? And what if the vaccines are not perfect? They only work with a certain probability. And what if the time you may remain infective exhibits only a probability distribution? So all kinds of things to make these models more complicated and more realistic and more interesting. And what about quarantine? Can you use graph theoretical models to analyze the effect of different quarantine strategies? Well, that's something that has been studied, for instance, in the context of power outages and quarantining part of the power grid where there is a disruption. So it's something we might learn about. Again, an analogy. We had one analogy between disease and fire spread, and now another between protection against power grid outages and disease. So there is much more analysis of a similar nature that can be done with graph theoretical models. And I'd like to thank everyone for the opportunity to be here for Boris Mirkin's birthday. And Boris, I wish you good health, many more successes, and all the best from your friends across the ocean, and congratulations.
Thank you. Do you have time for questions? No questions. Again, thank you very much, Fred.
It's my pleasure.
Thank you. Have a great day.
And you too.
To say some warm words to Boris and to present your talk. We are really appreciating your participation. Thank you very much again.
Thank you so much, and it is my pleasure and honor to participate here in this beautifully organized meeting dedicated to my dear friends and collaborators, Boris Mirkin, 80th birthday, and I sincerely thank the other Boris Golden-Gorin for making it happen. And now I will try to share my screen with you. Do you see my screen? Do you see my screen?
Yes, very good, very good.
Very well. Very well. Oh, sorry. 1 second. Let me just get laser pointer. 1 moment. Here we go. So, again, happy to speak at this meeting. And what I am going to do now is something quite unusual, I would say. I will talk mostly about a piece of work that we have done with Boris, with him playing Boris Mirkin, him playing the main role 20 years ago. More or less to this paper was published 20 years ago, more or less to the day. I think it's very typical of Boris' works that it is precise. I'm not claiming that I am precise, but I think Boris is. And I will try to explain in the next few minutes in this presentation. So this is about the LUCA, Last Universal Cellular Ancestor. The paper that we published back 20 years ago was dedicated to the reconstruction of the genome, gene set of the LUCA. And I will briefly explain to you how we did it and what happened, how our thoughts and ideas have changed during those 2 decades. But of course, to begin with, we must introduce LUCA and answer this crucial question. Are we actually confident? Are we sure there was a LUCA? Well, I will give you a resounding yes. There are several arguments for that. One of which, a powerful one, is the near complete universality of the genetic code, with small secondary deviations only evolving in some organisms, mitochondria, etc. The existence of about 100 universal RNA and protein coding genes, which are happen to be mostly component of the translation and the core transcription systems, which are actually involved in decoding that very universal code. And there are many additional broadly, even if not universally conserved genes, leaving no doubt that the heretical thought expressed by Darwin in the middle of the 19th century was right on the mark. LUCA definitely did exist. The fact that it did exist, however, doesn't make it easy for us to understand what it was. And the main hardship, the main difficulty in understanding this is illustrated by this slide. So if there is a tree of life, LUCA is at the root by definition. And reconstructing the genetic composition of that LUCA would have been a straightforward exercise, which we could do trivially by maximum parsimony if the evolution of life was indeed fully tree-like, as actually many people thought in the pre-genomic era. But in the genomic era, it has become very clear from the studies of many, many groups, even my lab participated in that, the evolution of life is very far from being completely tree-like. There may be, we believe there was a central vertical trend in this evolution, but horizontal gene transfer of genes between these different branches of the tree was truly rampant, making all kinds of reconstructions challenging tasks. So let us see what we have done. This is the paper that I mentioned in the very beginning by Boris, who did the main heavy lifting, by Trevor Fenner, his colleague then in Birkbeck College, by Michael Galperin from my lab and myself, algorithms for computing parsimonious evolutionary scenarios for genome evolution, the last universal common ancestor, and dominance of horizontal gene transfer in the evolution of Fokker. It's very long title, but we did address all these questions in that long paper. So the substrate, the source for reconstructing evolution are the what we call phyletic patterns of genes. That is, patterns of gene presence and or absence in the branches of the tree of life. Here I show the examples of universal and non-universal patterns. And the task of any reconstruction is to derive from these patterns the most likely ancestral states, and the most likely evolutionary scenario. This can be done by different methods, but primarily they fall into the families of maximum parsimony methods and maximum likelihood methods. In this paper, we applied a particular modification of maximum parsimony. With such simple trees, it's easy to see, as illustrated in this simple slide, how one reconstructs the ancestral states and the evolutionary events that result in the observed patterns. Here, for instance, in these two trees, we have just gene birth, one at root, which may not even count as an event, depends on the convention, and the other in the other case, here in this internal node. If you have a slightly more complicated pattern like this, you reconstruct two events, the birth of the gene and then loss in one of the branches. The thing, however, is that for many, if not most, phyletic patterns, different equally parsimonious scenarios with a minimal number of events can be reconstructed. For some of these patterns, many such equally minimal scenarios, like illustrated here in the simplest case, where there can be the maximum parsimony scenario involves two events, but these can be two birth events, like shown here, or a birth and death event, or gain and loss of genes, as we call it. So what we developed here with the main contribution from Boris is sort of a generalized parsimony approach, which does what any parsimony approach does, mapping phyletic pattern of a cluster of orthogonal genes onto a species tree, which is constructed from those universal genes that I have mentioned in the very beginning. And from this pilotic pattern in a bottom-up manner, reconstructing the scenario of evolution with a minimum number of events, the maximally parsimonious scenario. So we introduce here just a simple wrinkle that, however, is very, as we shall see, is very important, and that is weighted parsimony. We weigh the elementary events differently by introducing a gain penalty, which is really the key parameter of the algorithm. I should mention actually that in that paper, unusually for this kind of work, Boris actually proved some theorems about the properties of this methodology. But of course, we will not go into the proofs now. We don't have the time for that. What I want to justify are the values of this gain penalty. In the reconstructions of the evolution of prokaryotic genomes, we actually observe the dominance, preponderance of gene loss events. Perhaps counterintuitively, the number of, in most branches in the tree, the number of losses substantially exceeds the number of genes, of gains, such that to a very large extent, the evolution the evolutionary history is a story of simplification, gene loss in many lineages. I illustrated here by extensive reconstructions from our later work, but already at the time we published that paper with Boris 20 years ago, it was more or less understood that gain are sort of more difficult, less common than losses in microbial evolution. And therefore, we values of the gain penalty which we explore there greater than 1, from 1 to 15 or so, and the reconstructed size of the leuka genome depends, understandably, on this gain penalty, and at low gain penalty is also, again, very easy to guess. We reconstructed simple leuka with very small genome, and the subsequent evolution dominated by horizontal gene transfer, acquisition of genes by horizontal gene transfer, whereas and then with the increase of the gain penalty, the reconstructed size of the leuka genome monotonically increases, reaching, interestingly, values of about 2,000, a little less, which is very typical of modern prokaryotic genomes. So, in a nutshell, this is what we have done 20 years ago. What happened next? Actually, I did some literature survey while I don't claim it's while preparing this talk. I don't claim it's comprehensive, but I tried. And I cannot say that I found very much. Actually, some people used parsimony. Some people developed maximum likelihood, reasonably sophisticated maximum likelihood approaches. In the latest paper from Bill Martin's lab that actually received considerable publicity, they strangely used a very primitive, simplified parsimony approach, maybe because they used lots of data, I'm not sure why. So this came up with a very small size of leuka. This these approaches, both parsimony and maximum likelihood, came up with larger sizes from the bottom to the middle of the range that we reconstructed with Boris. But none of these approaches really, one of the maximum likelihood methods also gave a range, but a smaller range. So really the progress has not been so dramatic, even though I showed you the citation data, perhaps modestly, but we don't have to be modest for this celebration. I showed you the number of citations, which is almost 500 for that paper. So people sort of accepted it, but not that much progress has been made. I think we can still actually rely on that paper. There is an important addition in our understanding of Luca that I will describe in the last few minutes of my presentation today. Namely, there is growing evidence for highly complex Luca in the range, indeed, of existing known prokaryotic genomes. And here I want to briefly talk about an exercise that we have done recently with my colleagues on the reconstruction of the virome of Luca, of the viruses that that probably infected the Luca. So basically, you do it in a similar manner. You map different viruses to their hosts belonging to different branches in the tree of life. As you see, this is bacterial, this is archaeal tree, and it's a rich picture. There are many viruses distributed across many groups. So this translates into the reconstruction of a highly complex Luca virome that already included the majority of the currently known principal groups of viruses, in particular the famous tailed bacteriophages, small single-stranded DNA viruses, and quite some others. So we at least interpreted these findings as some indication on the nature of the Luca itself, namely suggesting the high complexity of the Luca. These observations, we say in this paper, imply that the Luca was not really a homogeneous microbial population, but a community of diverse microorganisms with a shared gene core, which was inherited by all descendant life forms, and a diversified pangenome. So this is one of the arguments for high complexity of Luca. There are other arguments which I think are strong. In particular, it's clear that Luca had already the nearly complete translation system. Almost all the components that are present in today's organism were already there, including the huge diversity of RNA modifications. There is another conserved component in the signal recognition particle, which is universal, which necessarily was present in Luca. And so the mechanism of protein insertion into membrane with signal peptides already existed. Then another line of evidence is actually the observed consistently dominance of gene loss in evolution of prokaryotes. This may seem counterintuitive, at least it did to me before I got used to it. But the thing is that much of the evolution from Luca on actually involved simplification, streamlining, loss of genes. So all this converges, or all this biological argument converges on the high complexity of the Luca genome, suggesting it was not really simpler than the typical modern prokaryotes. So in this range that I showed in that review paper written on the heels of our work with Boris, the real, our best idea of the actual Luca is somewhere here on top of the range. And I strongly suspect that while we have to still figure out the details, that conclusion is quite unlikely to change. Here it belongs, the actual Luca, I believe. This is what I wanted to tell you today. So very simple conclusions, growing evidence of the complex prokaryote-like Luca, indicating that the upper bound of the estimates obtained back in 2003, 20 years ago, they were straightforward, but flexible, because we introduced this key parameter, the gain penalty parsimony approach, reconstructing something like 1,800 genes, that upper bound appears quite a realistic estimate of the actual complexity, actual size of the Luca genome. So Boris, I think our work stands, and happy birthday and more success. I'll be delighted to answer any questions if you have some. Hello? Hello?
Hello?
Yes, hello.
Yes, thank you. Thank you very much again. And here our applause for your great talk.
Thank you.
One question.
Please.
Please, hear the microphone.
Thank you, Professor Koonin. The main concern is how is guaranteed that you find that Luca is unique? It seems that all these three models suggest many solutions, even under some constraints.
Well, that is surely a very good question. And there is no, okay, there is a universal core of genes about which I think, or near universal, I should rather say, about the uniqueness of which we should not really have. And that's not 100 universal genes, that's more, at least a couple hundred more genes that are so widespread that there is no ambiguity in the solution. Other than that, of course, I gave you only the quantitative approximation, numerical approximation of the complexity of the Luca. The qualitative reconstruction for the when the genes that are not close to universality are concerned is a different and complicated issue on which we still have a lot of work to do.
Just one more question.
Please, please.
One more question. Thank you very much, Eugene. Thank you very much for this wonderful presentation. And a couple of years ago, when I was reading your book of Logics of Chance, I understood that the concept of evolutionary tree was more or less irrelevant to the process of evolution. Can you tell me now What do you think of this? Is it relevant or not?
Okay. The concept of evolutionary tree is absolutely relevant for understanding evolution. And I'm sorry to say that if you read that message, the opposite message in my book, I'm afraid that it was either not very good reading or not very good writing or both. So, in fact, for each gene, the tree is the most natural representation of the course of evolution. Think of it simply in terms of replication. After all, the entire evolution proceeds by binary replication of genes. So for individual genes, absolutely, trees make sense. Now, what horizontal transfer does is disrupting the compatibility, disrupting the conservation of topology in the trees for different genes. So a far more difficult question is how relevant is any kind of consensus tree, anything like a tree of life. To this effect, there are different opinions, but at least from the work that we have done, we actually, some 10 years ago, so undertook a significant effort in just testing the tree hypothesis, testing whether or not there is a central tree-like trend in the, so to speak, forest of the trees of diverse genes. And I can say quite unequivocally that such a trend is recoverable. It is a statistical trend indeed, but there is a preferred topology. And after all, you know, then the dust settles. The classic ribosomal RNA tree is not that bad. It certainly does, by no account, does it describe the entire evolutionary process accurately. And it hardly can be. There is no good justification for calling it the tree of organismal evolution, but it is a central trend in the evolution of thousands of individual genes.
Thank you very much indeed.
My pleasure.
Thank
Good
you.
questions. It's
later.
very pleasant to answer such good questions.
Thank you very much, Eugene.
And thank you so much.
Our next speaker is Maria Poptsova.
На себя можно пришпилить. Так, скажите, пожалуйста, на каком языке говорить, если у нас иностранцы среди слушателей? Или you are, right?
But if I'm low enough, I will
No.
try to understand it in Russian too. But of course, in English it would be.
Yeah.
Well, it's
Well.
up to you. You are.
Okay. So how How shall I switch the slide? Okay, yeah, I'll speak English. Thank you. Thank you so much for the invitation. It's my honor to present here at this conference in honor of Boris Mirkin. And I'm doing bioinformatics, and Boris Mirkin also did bioinformatics analysis, and I collected some of his seminal papers. And Eugene Koonin just mentioned the work on his contribution to the field. And we never worked together, but actually at those time, approximately in 2005, I arrived at the University of Connecticut to the lab of Dr. Peter Gogatin to work on algorithm of selecting orthologs and paralogs. There was a NASA astrobiology grant, and I actually, at the same time, at the lab of Eugene Koonin, they developed the approach called cluster of orthologous genes to select, to distinguish between paralogs and orthologs. And my task actually was, when I arrived to the Peter Gogatin lab, my task was to select orthologous and paralogous groups for the given set of bacterial genome that were not represented at those time at the cluster of orthologous groups developed in Eugene Koonin labs. And I did a lot of phylogenetics. We also published so-called branch cluster approach, when I have to kind of climb up by trees and apply fuzzy logic algorithm to distinguish between who is orthologs, who is paralogs. That was my work at this time, and in that sense, at those years, we worked on the same subject with Dr. Boris Mirkin. And this is his work, and I devoted my talk to his birthday. But then later on, I switched on to the other subject that I would like to present today, namely DNA secondary structure, which I consider as some kind of encoding, a level of encoding, and I'll explain now in that sense what I'm talking about. Let us consider cell as a computer, as a biological computer, and genome as a genomic or genetic program that runs on the hardware, which is a living biological cell. And then when we think about the program, and when we think about the genome as a program, then we need algorithm that somehow are encoded in the genome. And this algorithm I encoded in the genome, and DNA is a hardware. And DNA, just remind to those who are not from the field, that we have DNA, and our genome is composed of DNA, and DNA packed in a chromosome that we can see under the microscope, and the packing is multi-level, and it's wrapped up about nucleosomes. Nucleosomes are packed, and then it is packed, and DNA becomes 700 times larger than its initial size, and this all organized so that at some time, at some point, some part of the DNA are accessible and can be so-called executed in terms of computer algorithm, and some are hidden, and it is all regulated. And we can theoretically approach it as a level of genome encoding. So when we think about the genes, and these are pieces of DNA that are converted to a protein, and proteins are molecular robots that do all the works in our cells. And there is a algorithmic encoding. There is a genetic code that, according to the rules, convert piece of DNA into language of proteins, which are composed of 20 amino acids. And there are some other regular elements that are encoded in a linear manner, that's so-called DNA motifs. And we consider it as a first level of genome encoding. But we have the same genome in every cell, and the cells are different. There are lung cells, brain cells, etc. All types of tissues are represented by different types of cells. And there is the same, exactly the same DNA in each cell, meaning that this level of DNA, this text, genomic text, are the same in every types of cells, but cells behave differently. And this regulation is done by epigenomics. It's from the Greek word epi, above. Genomics is a genome, meaning that there is some program that regulates the work of this genetic program without changing the DNA itself. So this is, that's why it is called epigenetic, and it is realized by specific biochemical markup. So you can imagine, as we put some flags or markers in the book of the text and saying, if there is this mark, this piece of code would work. And if there is a combination of this mark, it should work on that or that occasion. So it's all algorithmically, and it's a very complex combinatorial markups with the histone marks, transcription factor binding sites, chromatin packaging, methylation, etc., etc., and accumulate. We have access to that due to the advances in experiments. So we have the 21st century produced a lot of so-called next generation sequencing technology that allows to measure all these different markups, and they are accumulated in public database, in private labs, and it's cumulatively, we would call a second layer of genomic encoding. And there is a third layer of genomic encoding, which is DNA secondary structures, which is main interest of my lab, and how it works with the second layer, with the epigenomic layer. Imagine you have a DNA as a DNA strand, and you can have like a beads on a thread, like beads on a DNA, that are composed of three-dimensional structure. These are real three-dimensional structures. Could be, they have different names. One is DNA is wrapped, so it's not just something special that is set up on a DNA. It's a DNA is wrapped itself to make this three-dimensional structure. It could be quadruplexes. It could be the name. It's like a parallelogram with the letters G in each corner of a parallelogram. It could be triplex when DNA is a double-stranded and there is a third complementary piece of RNA or DNA goes up together. There is a zDNA. zDNA is a DNA, the DNA that, say, Watson and Crick got Nobel Prize, is a so-called bDNA, right-handed DNA, because DNA is a spiral and it has orientation. And later on, in 1979, by Alexander Rich in MIT in Boston, discovered another form of DNA, left-handed DNA, and it called it back in 1979 as zDNA. I would like to change its name now to left-handed DNA. Left-handed DNA, but the name is just set up, and from that time, for some reason, it was called as zDNA. And initially, people thought that it's just artifact of experimental settings. But later on, his postdoc, Alan Herbert, discovered a protein that binds to these zDNA left-handed short regions. And meaning that there is a protein, there is a molecular robot in the cells that binds to this region, implies that it's biologically important and have some function. So it's another piece of DNA structure that served as some regulatory elements that has some function. And having all these layers together with all these experimental experiments that are available at the genome-wide level, we have many, many layers of encoding. And all these multidimensional data, unfortunately or fortunately, our human brain cannot, be used to find all this association. That's why we use deep learning approaches. How do we do it? Actually, machine learning and bioinformatics is utilizes already approaches that were successful in some other areas. So we don't have much, bright, intelligent minds who developed algorithms specifically for bioinformatics tasks. Because all these, IT minds, they are employed in other more practical areas as, image recognition, machine translation, other practical tasks. What we use, we just take ready-to-use solutions. For example, some machine learning architecture showed good performance in some other areas. And people say, okay, let's try to somehow apply it at the genome-wide level. The same happened initially with convolutional or recurrent neural network. Convolutional neural network first showed a great success in image recognition. And how can we apply it to DNA? And what we can do, we can somehow transform information in DNA into the matrix-like representation. The very easiest approach is to use just binary representation. The name is one-hot encoding. When we represent DNA as a matrix of length L and depth number of letters. Here we have just 4 letters represented DNA, and if we want to talk about the regions of 500 letters of DNA, we are talking about matrices of 4 rows by 500 columns. And surprisingly, and then we have a binary matrix, and then we can train CNN on this binary matrix, and surprisingly, it was very successful in recognizing many functional elements initially, but it did not work. So we applied it to quadruplexes, and it worked very well. And people applied to recognize its transcription factor binding site and recognizing these elements from the second regulatory epigenomics layer. It did not work for us in our lab for recognizing zDNA. That's why we extend, so the idea was that there is no signal in sequence itself to recognize this particular left-handed elements, and that's why we try to collect more information from so-called omics data. Omics data is in molecular biology nowadays is cumulative name for transcriptomics, metabolomics, epigenomics, all this omics meaning the cumulatively all the available experiments that we have now to find the location of this or that regular elements. And that's what we did. We collected as much information as we can for defining zDNA. We collected histone marks, transcription factor binding sites, more than 30,000 experimental data that was available. We added also biophysical properties of DNA in that region, B to Z transition energy, and we first developed our approach to predict this region based on CNN, which is convolutional neural network, and RNN, recurrent neural network, that at those time were the leaders in machine translation. And also you can deal, these are advantages of DNA. It can be either represented as a image or as a text, and we can try both. And we actually, these are information about omics data that we use, cumulatively more than 30,000 experiments that were collapsed to 1,000 plus rows that were added to the binary matrix. It's already not the binary matrix, and binary plus some real number from these experiments. And that was successfully, and we published this approach in 2020, 3 years ago. And then these are experiments where we took the data to train on. There was, at those time, they're called ChIP-seq experiments. So you can throw up a protein, and the protein binds to DNA specifically to the region of interest. And it's called ChIP-seq experiment. There was one experiment, at those time, there was just one experiment detecting zDNA region at the genome-wide level, made by Korean scientists. This was published, that was available. We trained our data on that. And also, I won't go into the details of that experiment. There was another experiment also helping to detect the entire range of DNA structure, including zDNA. And that's how we choose between architectures. So we tried CNN, we tried RNN, we tried hybrid that showed. So you just combine two architecture, and then we estimate, we run around more than 150 different experiments to choose the best one, and from that we see that actually even though the RNN was the best at those time, the difference is not that considerable that we can choose one on another, but we showed that approach is applicable, and with that we can generate the whole genome map. Later on, another laboratory generated the whole genome maps of zDNA on mouse genome, and we participated in that experiment. The paper was published in Nature last year, because we showed that this laboratory specifically explored the mechanisms by which the anti-cancer drug kills the cell, and it appears so zDNA, one other function of zDNA is that it can switch cell to the death pathway, and there are variety of death pathway cell can finish its life, and one of the is a necroptosis, and actually we showed that you add a substance called corexin, it induced a lot of zDNA region that is a signal for cell to die through this pathway, and we did all bioinformatics analysis, and by that we got a lot of data on zDNA to generate to train our machine learning model to predict it in other cell types. And by that time, you know, in the other fields, say in the machine translation and image recognition area, everybody already knows that transformer beat at both CNN and RNA, and that is why we also made a step forward and try to apply transformer models. And here is the difference between approaches. So you can see that, well, RNN is good when you would like to catch up long-range interactions. CNN is nice in distinguishing context, and actually if you have a regulatory motive, it doesn't matter where in your matrix this important motive is located. CNA is independent on the location, and transformer is good that it captures the whole range, long-range interaction, and also is not dependent on the precise location. And in transformer area, again, the choice and many successes was for the pre-trained models, so-called BERT approaches, and in our bioinformatics field, people already created so-called DNA BERT. Not so-called, it is named DNA BERT. So people pre-trained transformer models on the entire genomes, both human and mouse, and we just took this DNA BERT, and when you have the BERT approach, it's good that it is pre-trained on a general task, and then you can fine-tune it to your specific task, and that's what we did. We took it, this is how transformer is trained. We used tokenization. DNA is tokenized into chimer, and DNA BERT was pre-trained from 3 chimer up to 6 chimer, and of course we took the latest, the chimer representation, and then we trained, we call it zDNA BERT, and you can see on the right, you can see the attention maps which are generated by transformer algorithm, and this you can see the red region which is marked. It is our zDNA, and you can see, when you visualize this attention map, and there were 12 layers of attention in our models, you can see, you can visualize how transformer learned to recognize these particular regions of our interest. And in science, it's for us, it's not only important, to have a model that have a highest performance score. It is always important for the interpretation, because from the interpretation we can learn, we can gain many biological insights, how the model learns, what are the important features of this model, and this is just example of this transformer model interpretation. And what we generated the whole genome, the whole genome maps of the DNA compared with our previous approach, and showed that now, surprisingly, this approach did not require this omics data. It was enough to have just DNA sequence, so was independent of additional information, showed extremely good performance, and then we explored the many functions of that of the predicted zDNA region, and discovered that actually mutagenesis in our genome, and we know that from many genome-wide association studies that one letter, changing of one letter in genome can be associated with many diseases. And the principle of whole genome association study, and when you take many healthy people, then you take the same amount people who has certain phenotype, often disease, and then you do genome-wide sequencing, and then you compare, and statistically you find associations, say, of one letter change with some disease. And there are now numerous databases that publish this result of the studies, and we exploit this knowledge and compared how all this our predicted zDNA region overlap with these genome-wide association databases, and found that quite a number of mutations associated with diseases is also associated with this zDNA region. and I probably won't go into details of this biological analysis, it's too much. We just, it's a very recent, our research, it just published on bioarchive, and it is undergoes revision into the journal. It is not yet published. It's very new, and this work has been done in collaboration with Sber Artificial Intelligence Lab. The first author who developed the transformer model is Dmitry Umerenkov, and his co-author Vladimir Makarenkov. They are from Sber Artificial Intelligence Lab. And I think I'll finish now. Just
Any questions? Please. You said about propellants and aeroplanes, and one of your papers is about propellants and another about aeroplanes. What are the approaches with propellants and aeroplanes?
No, it was I just mentioned actually not mine work. I should this was work of Boris Mirkin, but I did work on prokaryotes. Prokaryotes doesn't have this layer of complexity, say, as epigenomic markers. It's just the genomes are smaller, and you don't have this epigenetic regulation. You don't have nucleosome that's wrapped up. You don't. That's why you don't have markups. Though in some you have maybe a little bit more complexity than just the DNA level. They have a packaging of a chromosome, not though in nucleosome, but in chromosome loops. But in terms of our approach, we cannot apply omics data to prokaryotic genome. We need, if you want to predict some regulatory elements in prokaryote, you have to consider only DNA sequence.
What you mentioned about visualizing the attention, have you by chance applied the Shapley values or the Shop library to determine the importance of features and compare it with these methods which you use for visualizing the attention?
We, in general, that's why I since you asked, I skipped the whole section. It's really important, this explainability, and a neural. So for CNN, you can visualize activated filters. Maybe you know, right? So an activated filter we transform to this like motif that you see. To generate satiety importance, as you see on this graph, is a classical machine learning like random forest. Another, we did a trick with regularization on the first layer and see dropout of the coefficients, but it's very kind of not as straightforward. RNN is almost uninterpretable, and this is the direction that we develop in my lab and try to apply. It's very interesting. Its approach was done in these, the first author is Lapushkin, who is obviously a Russian name, but he doesn't speak Russian, and he works in Berlin. And his approach is a layer-wise propagation that I'm trying to apply now to our omics matrices. To apply his libraries, it's already ready-to-use library that were developed for multi-layer perceptron, fully connected neural networks that shows the regions to where the neural networks pay most attention to recognize images. For example, he shows that neural networks fail at recognizing that this is male, and but human doesn't, right? So these are and shows artifacts that, for example, with this approach, you can see that neural network can be trained to recognize ships just by recognizing that there is a boundary between sky. And I'm trying, so for me, the matrix is my DNA plus omics data, which has specific biological meaning, and applying these maps to omics data, I would see what are the important elements of epigenetic codes that was important in training neural network. This is a work in progress. That's why I skipped it. Sure.
Any more questions?
So what percentage of information is hidden in epigenomics as compared to the DNA structure?
I think much more, because you see we have, so DNA is a DNA, 4 letter, and that's it. Yeah, and 3, yeah, entire spiral. Then epigenetics have at least 50 different histone marks that can be present in one location of DNA in combinatorial manner. So one position of DNA can have up to 10 different histone marks, which would signify some specific signal. Histone is a nucleosome. It's like what is called katushka, thread wrapped around cylinder, right? And on this cylinder, not on the DNA, but on this nucleosome, you can, because it's composed of proteins, you can put up to maybe even 10, 15 different marks, and independently, yes. And epigenetic code is not stable. For example, it can be changed during the life, and it is changing, because for example, how we develop. At one point, we just one cell. We were one cell, existed, stayed there for about 20 minutes in one cell. Then during the first week, we develop in a ball where every cell, 100 of cells, and every cell is exactly the same, without any difference. And epigenetic the same. At a certain point, when differentiation happens, different cells acquire different programs. So we have to switch on and switch off different programs, which is controlled by epigenetics. DNA stays the same. It should be reprogrammed so that one part of the cell became, your head, the other part of the cell became the tail, etc. So embryonic development is already reprogramming of many, many genetic programs.
So then we come back to this story how it exploded in science. When, when a horse having partner with zebras continue to produce striped horses when matched with another horse, because of epigenetics. No, it's not possible.
I think it's much more simpler than epigenetics. Epigenetics is, yeah, so epigenetics, it's reprogrammed. Another level is not histone marks, say methylation, just DNA methylation. It's like a commentary on your code. So just straightforward showing that this part of the DNA works and this does not. And methylation level was shown correlated with age. So just measuring methylation level, some startup companies now estimate biological age of a person, just methylation level, just of DNA. Good point.
Thank you very much again.
I will start. It's a real pleasure to me to present at this conference dedicated to 80th birthday of Dr. Boris Mirkin. I first met with Boris, it was about 25 years ago at the North American Classification Society conference in Montreal. And after it, our collaboration continued through the years. I really enjoyed the time when Boris with his students came to Montreal. It was about 5 or 7 years ago with Renato de Amorim and Andrei Shestakov. And this visit resulted in 2 nice papers published in Information Science and Pattern Recognition. And I hope our collaboration will continue in the future through the years. My today's talk will be dedicated to 2 topics of Boris' interest. It concerns evolutionary trees first and clustering second. So we are trying to combine both of them and to find clusters of trees. In fact, you can cluster everything, documents, planes, and you can cluster trees as well. And this is the topic of my talk today. This is a joint work with my student Gayane and Nadia. Nadia, she is now a professor at University of Sherbrooke. But when we started to work on this, all of them are in the University of Quebec in Montreal. So it's the presentation of my talk, summary of it. I will first introduce main definitions and basic facts about phylogenetic trees or evolutionary trees. Then I will talk about consensus trees and super trees. After it, we will move to tree clustering, and I will describe some or present some tree clustering methods used in science. And finally, I will finish with the application of tree clustering in the field of evolution. First of all, what is phylogenetic tree or evolutionary tree? It's a tree showing, it's a kind of branching diagram showing the evolution of a group of species. And the species in this tree, we have different kinds of nodes. We have leaves. Leaves are usually associated with some contemporary species. And we have branches that represent the process of evolution. And we have internal nodes that represent common ancestors of species present in the diagram. And we have the root. And the root is the common ancestor of all species present in the tree. Boris Mirkin worked a lot in the field of evolutionary trees, and just these 4 papers were cited 2,659 times. It's, up to date. It's about the evolution of a different. In fact, Boris modeled a lot the processes of horizontal gene transfer, gene loss, and other supplementary reticulate evolutionary processes that complement the straight evolution. And there are some famous papers that are really seminal papers in the field that we can mention here. 3 of them resulted from the collaboration with Dr. Koonin, and 1 of them with Dr. Smuchnik and Smith. Now I will show what is a phylogenetic tree from the mathematical point of view. For example, we have a tree on the right, and this tree have 5 leaves. It represents 5 species, and we have some distances, some weights on the branches. And this tree also is called additive tree or X tree. Additive tree, why it's called additive tree, is because, for example, the sum of the branch lengths is located on the path between species X1 and X2 is the sum of 1 plus 2 plus 2 plus 1, and it gives 6 in the tree matrix a matrix located on the left, shown on the left, and this is the value, the corresponding value for the distance between x1 and x2 in the matrix. So we have some different kinds of trees, and in fact, when we are working with with evolutionary trees, usually we construct one tree per gene. We can also construct a species tree for genomes of species, but when we work on the gene level, we have different trees for different genes, and always question is to the problem is to reconcile those trees, and to represent a kind of consensus tree that represent best the evolution of all these trees. And there are different kinds of consensus trees. For example, strict consensus tree that considers only on the splits or only the branches that are identical in all trees. Every branch or every edge introduces a bipartition in the tree. We have also majority rule consensus trees that are much less strict than consensus trees that include only splits that appears in most frequently among all the trees compared. The threshold that is often used is 50%. So every branch that appears in more than 50% of trees will belong to the majority rule consensus tree. We have also extended majority rule consensus trees, that it is a continuation of majority rule consensus tree, and the Nelson consensus trees that include the heaviest set of compatible bipartition. But to construct a Nelson consensus tree, the problem is in big hard, so we don't have, at least so far, a polynomial time algorithm that allows us to solve this problem. I will show an example of a majority rule consensus tree. We will mostly work with this kind of consensus trees in our talk. And here we have an example of 3 trees: T1, T2, and T3. And we can observe that T2 and T3 are equal, identical. And this means that all branches appearing, we are looking for internal branches mainly in these 2 trees, they will belong to the majority rule consensus tree. So even though the tree T1 is different, the main attention will be to T2 and T3, and the consensus tree of these 3 trees will be in fact the trees which is identical to T2 and T3. We have exactly the same topology here, because all splits appears in 2 trees out of 3. We have also the problem of super trees, so-called super trees, when we compute trees defined on different set of taxa. So far, what I have shown, it's for majority rule consensus tree, all terminal nodes or all leaves of the trees were identical. It's A, B, C, D, E in all 3 trees, maybe in different order, but the same set of taxa. But here we have also the situation in evolutionary biology when the taxa are different. They are different but mutually overlapping. So there is some overlap, but in fact sometimes we don't have the information from some species for some genes, so we cannot infer all genes for the same sets of species. Sometimes it's some partial overlap occurs. So in practice, we have rather have to deal with super trees rather with classical consensus trees. And a super tree is a single phylogenetic tree assembled from a combination of small phylogenetic trees. So I gave here an example. So we have trees defined on different but partial overlapping sets of species, and we try to combine everything and find a kind of consensus tree, but in fact it's a super tree. It will represent all species present in all trees, but only once one species will be present only once, but in fact it will combine the main features of all trees present in the input data set. Now I will talk a little bit about the evolutionary mechanisms that require a gene tree reconciliation. Here we have horizontal gene transfer when there is exchange of genetic material between different species, between different genes. Here we can also mention hybridization, recombination, homoplasy, and gene duplication followed by gene loss. And there are two ways to represent this kind of contradiction, as I would say. It's either to present it either as a network, as a phylogenetic network, or as a combination of trees, so by clustering the trees. I will not talk today about phylogenetic networks. It's one way to represent conflicted elements, conflicts between genes, genes representing the evolution of a certain group of species. I will rather talk about about clustering of genes. What we can do. We can, if we have, for example, gene trees for a set of species, we can cluster them, and these clusters will represent the main trends, the main evolutionary trends, accounting for the evolution of this species. In fact, here is just one example. When we group it together, some genes of coronavirus genome, and we obtained three trees. Each of them is a kind of consensus tree, and each of them represents some main trends of the genes included in this cluster. For example, the first tree is the consensus tree of the genes ORF1AB, S, RB domain, and N, and so on for the other genes. What's important to know here, it may represent, for example, it will cluster together genes that had similar evolution, that underwent the same horizontal gene transfer, or the same gene loss events, and so on. There are a lot of literature about clustering in general, and I would like to highlight these two books of Boris Mirkin. It's a real classic, really seminal works that I should recommend to everyone. And as I said, the topic of our talk today is clustering of trees. Here, instead of objects, we are each object, it's one tree. It's one evolutionary or one phylogenetic tree. And in the beginning, we have a set of scattered trees, and in the end, we need to group the elements and to find the cluster. Here we have three clusters of trees. And the choice, the obvious choice, some important choice that we need to make before starting clustering elements, it's a choice of cluster centroids. And in the case of tree clustering, it's we often select as the center of a cluster a majority rule consensus tree. It can be another kind of consensus tree, but often it's a majority rule consensus tree. And the choice of distance is also very important, and the distance between the elements, because here, when we work with trees, we cannot apply some traditional distances like Euclidean distance, Manhattan distance, or Minkowski distance. Here we need to work with distances that are proper to the field of trees, that are proper to the field of computational biology, and the distance that we selected and people use often in general, it's the Robinson-Eifeld topological distance. I will give its definition right now. In fact, if we have two trees, two evolutionary trees defined on the same set of species, the Robinson-Fultz topological distance between them, it's the number of elementary operations that consist of splitting and merging its nodes that are necessary to transform one tree into another. Another equivalent definition, it's also the number of bipartitions or Bunneman splits which belong exactly to one of the two trees. So for example, of these two trees, we have the Robinson-Fultz distance between them is equals to, it's a topological distance, it doesn't take into account the branch lengths, but what's important for this is it's only the topology. And here we can see that we can merge the node, this node with this one, and after it we can expand the node E, and so we need two operations to transform the tree T into the tree T prime, and the Robinson-Fultz distance between these two trees will be 2. This distance is also called the symmetric difference distance in the literature, and the important property of this distance that we will use in our clustering is that the square root of the Robinson-Fultz distance has the Euclidean properties. So here is an example of multiple majority rule consensus trees. It shows why the tree clustering is important. If we have, for example, 4 genes and 4 trees representing the evolution, it's trees T1 to T2, T3, and T4. The traditional majority rule consensus tree will be a kind of star tree. And here we lose all the information, all important information about the evolution of those trees, because we don't have internal branches here. But if we do the tree clustering, we can observe and take advantage of it. After it, we can see that trees T1 and T2 are very close to each other, and the same for T3 and T4. So we can organize these trees as two consensus trees. In fact, one tree for T1, T1-2, and one for T3 and T4. So, and those trees are much better resolved. We have 2 internal branches in both of them, and so we keep some important information about the evolution of those trees in the majority rule consensus tree. The same is true for the case of super trees. Also, if we have those trees defined on different but partial overlapping set of species, there are 7 species here associated to the leaves. If we apply the traditional method, we obtain a single majority rule super tree, which is a star tree. But in case of super tree clustering, we have 2 trees that are much better resolved and that keep some important information about evolution of the trees T1 and T2 from one part, and from the other part of trees T3 and T4. So I need now to mention some existing works in the field. First, it's phylogenetic islands method, and that was proposed by Madison. It was a method that divides a collection of trees based on their branch lengths. It divides on several clusters of trees, and the other used different branch rearrangement distances in order to find those islands of trees. The second method that I need to mention is the method of Stockham and co-authors. They used a kind of tree clustering very close to k-means, but the Robinson-Fultz distance they used, it was a squared one. I will show that it's not really correct. We don't need to use it in a squared form. And also the others use the strict consensus trees instead of majority rule consensus trees, and the strict consensus trees are very, I would say, very conservative, very strict, and usually these trees represent star trees. Also, we need to mention the method of Bonnard et al. That was published in Systematic Biology, which is a very good journal in the field. And but unfortunately, as for many methods, we don't have software that support these publications, and so it's difficult to reproduce the results of those research. So for the method of Bonnard et al., it's consisted in finding small sets of trees, including all splits whose support was greater than a predefined threshold, because for every branch, every split, we have a kind of bootstrap scores that represent the statistical support of the branch. Also, we need to mention the method by Genosh. Genosh came up with a kind of function, a kind of score function to be minimized. And also the main purpose of his method was to find whether a group of trees should be represented by several consensus trees or just one general consensus tree. Also a nice paper by Silva and Wilkinson, we need to mention it, that has recently appeared in Systematic Biology. The method was based on any appropriate pairwise tree to tree distance metric that expands the notion of island. So it was a kind of continuation of the work by Madison, of the first method that I showed. And now I will come back to the methods developed in our lab. Most of them were proposed with my former PhD student, Nadia Tahiri. And here in the first one, it was about 4 years ago, we proposed to cluster trees using Robinsonian false distance and K-medoids. Here we didn't use K-means, but here we used K-medoids. And the main results that we obtained, we managed to adapt such well-known cluster validity indices like Silhouette or Kalinsky-Harabat's cluster validity index to tree clustering with phylogenetic trees, because we cannot use a standard cluster validity indices to obtain the optimal number of trees for each data set. And here we used non-squared form of Robinsonian false distance, and in case of K-medoids, the center of each cluster was one of the trees of this cluster, which was the closest one to the center according to the Robinsonian false topological distance. In fact, natural way of clustering trees, it's to find a kind of consensus tree. For example, here it's a majority rule consensus tree, and to find a clustering that minimizes the following objective function. Here we have the Robinson false distance between all elements of each cluster, and we sum it up over all clusters. And the distance that we compute is between each tree of the cluster and the majority rule consensus tree within this cluster. In fact, the use of the Robinson false and false distance and not of its quadratic form is tree clustering is justified by the fact that the majority rule consensus tree of a set of trees is a median tree of this set in the sense of the RF distance. It was shown by Bartlemy and McMorris in 1986. And this fact means that we should not use the squared version of the RF distance as it was done by Stockham and Clansers. And finally, our most recent work concerns the use of K-means. It's K-means, Robinson full distance, and we used it for tree clustering. Here, the centers of the trees are, in fact, the majority rule trees, but we don't need to compute the centroids because this can take a lot of time. In fact, we use the property of the Robinson false distance, the property that it has the Euclidean property, and it allows us to transform the original objective function into this function, which is the sum of the RF distance within clusters. And this, in fact, the error distance can be pre-calculated before using the k-means, which allows us to save a lot of time. In fact, what we actually do, we pass from this original matrix, which is matrix of different vectors representing our entries, to the squared matrix like this. Because in the original matrix, we have each vector has a length of 2 power n minus 1 minus 1. It's it will take exponential time to treat to process such kind of matrix, and we pass to a squared matrix of size n by n. And in this matrix, we have only error distances, Robinson false distances that can be, as I said, pre-calculated. So in the whole algorithm, it will work. In fact, we pass from exponential space to the quadratic space, and this allows us to have to keep the time complexity of our method. It will be, in fact, the same as in traditional k-means. We don't increase it at all. In fact, it will depend on the number of trees and the length of each tree, so the number of elements in each tree. And at the same time, it will depend on the number of iteration in the internal loop of k-means and on the number of clusters k. Finally, the formula that I have just shown was extended to the use of super trees. In fact, it's the same formula, but here we use a kind of normalized Robinson false distance. So we normalize it by its maximum value, and we also add a kind of penalization factor, where alpha is the penalization parameter, and this is the version of the objective function that works best in our simulation, that provides the best results overall. In fact, I will show now an application of our method in the field of evolutionary biology. And here we treated the example of SARS-CoV-2 genes. It's well known that the evolution of coronavirus is very complex, and we still don't know the exact origin of this virus. But what was observed that for some genes, there are in fact 12 main genes in coronavirus genomes, and for some genes, the human SARS-CoV-2 gene is closer to the bat. In fact, it's RAT13 bat coronavirus, but for some other genes, it's much closer to the pangolin coronavirus. So it's a kind of recombined genome, and in fact, it was very relevant to apply our tree clustering method here to study the evolution of those genes and to see how the clustering can be applied here, and what are the main trends. What are the main trends of coronavirus genes that can be observed, and what are the clusters of genes that follow the same evolution of SARS-CoV-2 genes that follow the same evolution, maybe underwent the same horizontal gene transfer, same recombination, same gene losses. And it was the main purpose of our study here. First of all, we try to see. In fact, here we can see the picture of recombination of several genes. In fact, it's a genome recombination with of coronavirus genomes of several species, including bats and pangolins and SARS-CoV-2 of human. Also, we carried out a kind of it was a fit test that was executed here, a kind of recombination test, to detect a combination within each gene. And here we found that 7 out of 13 genes had recombination within it. So it's shows that there was a very, very intense interaction between those species and between those genes during the evolution. And after the application of our super tree clustering method, because for some species we had only partial overlap between the sets of tree leaves. We found, in fact, 3 clusters of trees here. First of them, it was this cluster regrouping species, regrouping genes EM, ORF6, 7A, 7B, 8, and 10. It was this cluster. We also have here some branch length support indicated on the branches. Then we also obtained the second cluster for the genes ORF1AB, S, ORF3A, and N, and finally the super tree for the RB domain, which is a very important domain. It's a part of spike protein. It's not a gene, but it shows that the RB domain is very important, and its evolution is very unique because we have only a singleton element in this cluster, but its evolution is totally different from the evolution of other genes present in the coronavirus genome. We also applied it to the evolution of languages, but I will not show it today. We also obtained some interesting results, and we have a work in progress on this topic. But in fact, in this paper published in BMC Evolutionary Biology, that received a lot of attention so far, we managed to show, in fact, that the evolution of genes, of coronavirus genes, are quite different, but there are some genes that have the same trends. That in this case, a lot of genes underwent similar horizontal gene transfer events. Okay, so the last thing that we have done for this data set, for coronavirus genome data set, we also obtained horizontal gene transfers for the trees. There are different because have different kinds of color for clusters. We also obtained some mosaic genes for this data set. And here is the final pictures that represent the main trends of evolution of these genes, of coronavirus genes, during at least 30 or 40 last years. It's the period of time for which we followed those genes. And we have that, we can see that it's quite divergent, and there were a lot of interaction, a lot of gene acquisition and gene losses during the evolution, and it needs to be studied further. So I hope our work will be continued in the future. And finally, I will present some references, some important references that I mentioned in our work. So there were some theoretical works needed to organize clustering algorithms, but also some evolutionary papers that we used in order to find the information about genes, genomes, and species. Okay, so thank you very much for your attention. If you have some questions, please ask.
Can we use Levenshtein distance as a reason of making closer or more far in this tree? Levenshtein distance of DNA.
Okay, but usually we use Levenshtein distance, but not for DNA data, not for evolutionary data. DNA distance, we used it to compare words. In an example, I didn't show it as this example, but there we compared some word trees. You know, it's words from Indo-European languages.
And DNA
but
also
but when we work with DNA, we have some distances proper to evolutionary, such as Kimura distance, and there is also Jukes encounter distance that are adapted to the tree evolution. Sometimes they work like Levenshtein distance, but sometimes it's different because it's the distance between different letters of genetic sequences between A and C is not the same that between A and T, for example. And we need to take it into account. So the Levenshtein distance cannot be used direct. It should be modified.
Yeah, thank you very much for a very interesting approach. I wonder, this refers to COVID. So if there is any substantive interest in building such a tree, is there any, I don't know, the treatment can be produced from it or anything? Thank you.
Okay. Thank you, Boris. In fact, there is general tree, which is that represents the evolution of genomes that can be inferred. It was inferred by several others for SARS-CoV-2 dataset for COVID. But what's important here is to understand that evolution of every of 12 genes of COVID is different. It was different, so some genes underwent horizontal gene transfer event, the other underwent some gene loss, the other underwent some recombination, and it was different. So it cannot be really represented as one tree because the evolution of some parts, some genes of this tree will be different. And if you represent it a kind of as a one tree, it will be an approximation, only an approximation of the evolution of the genes or genomes of SARS-CoV-2. In fact, what we are doing, the tree clustering, is also an approximation. But here we approximated by groups of similar genes that underwent the same evolutionary event. So it's a kind of approximation. But here we can keep all important elements and all we can after it. In fact, infer those elements. We can find these gene transfers that impacted the evolution of the COVID genome. Thank you.
Thank you very much, Vladimir. Thank you. Our applause for your participation.
Yes, thank you to everybody. Thank you, Boris.
So my question now to everybody, are you ready to continue with my talk, or if you are too tight, we can switch my talk for tomorrow? Today I'm going to talk about not really popular approach in data analysis, clustering, machine learning, and much more areas, which has a very simple approach based it's okay, based on pseudo-Boolean polynomials. The roots coming from allocation problems. One of them might be considered as a p-median problem, and it is not important. So if you have no idea what is this, I just give you an informal introduction. if an input matrix containing m rows and n columns, and as usual in data analysis, we have m objects and say n Nancy parameters, or how we call this in cluster analysis, too many synonyms, and you have fixed p rows only to use them as say center clusters, then the problem might be formulated as follows. Take from the given, in this example, say 3 rows, such a collection from m rows, such that the total distance, doesn't matter how you defined it, will be minimized. It can be easily written as a combinatorial formulation, where if I throw out the summation for any, say, column or customer in terms of the p-median problem, and for the fixed cardinality of the subset, which is in this case p standing for p-median, we take the nearest from available, say, capital S rows or potential places to place some equipment, and we sum up by means of all columns. And it is clear this formulation nothing to do with algorithms or data analysis, and I skip completely either complexity or some issues related to solving the p-median or some other allocation problem. What I am really interested in, just in the pseudo-Boolean formulation, and I will really spend enough time such that you will see why it is so elementary and underestimated by the research community, from machine learning and actually everybody who talked today, for many, many applications contributed by Boris and his colleagues. There are essential number of publications, but they most consider linear integer programming approaches with some advanced method for solving the p-median problem, and just a few, and I would like to mention in the first place Peter Hammer, 1968, and our colleague from Russia, Vladimir Beresnev, 1971. Now we come immediately to the essential example. I consider with 4 rows and 5 columns. Numerical example, you can say clients or parameters or dimensions, depending on the interpretation. And I would like to explain how for chosen rows 1 and 3, I'm going to compute the value of the objective function. As you can see, for each column I take just the smallest entry located in first and third row. And you can see they are circled by orange color, 7 plus 7, 6, 7 and 10. And you have, in fact, 37. This is the value. Now I'm going to introduce the same example in terms of the pseudo-Boolean approach. I consider, just for sake of simplicity, 1 column, since I'm going to repeat the same operations. I make an ordering in non-decreasing order of all entries in the first column, and you can see this is pi sub 1 permutation, shows that the smallest element is located in the first row. I talk still about the first column. And the next one, 10 in the second, then 11 in the fourth, and finally the largest, 16. And also I'm going to use a column related or associated to each, say in this case column 1, of differences. So we can't serve more cheap than the cheapest element. So at the first place, in this column of differences, which is denoted by delta capital C sub 1, I place always the smallest element. If there are many, it just doesn't matter. In lexicographical order, any of them. And then the differences. So where they're coming from, the next. If it is not available, the first row, then I'm going to use, oops, something I have touched, not intentionally. I apologize. I'm going to use 10, and the difference between 10 and previous one is 3, etc. Finally, you see the differences will be 7, 3, 1, and 5. Also, in an unusual way, we introduce the decision variables, Boolean, y, sub I, where we say a row I is available on object I, and in this case, y I is equal 0, and if not, then 1. And for the previous example, you see the y vector will be 0, which means the row first available 1, 0, 1. Now how we create the corresponding fragment related to the first column. We just take the smallest, we can't serve better, and then we add 3 times y1, which means if y1 is 0, then we just serve by the cheapest value. If not, we add. In a similar way, we go through the green indicated in this slide monomials, and we use just in the left bottom corner all differences, we adding them, so the last one will be 16 only in case if rows 1, 2, and 4 are not available. Then we just repeat for the second column, for the third, etc., for the first. As soon as we have done, and you can see it can be done in polynomial time, and it can be done much more faster, in fact by random, say, orderings, in fact in linear time. I'm not going to pay too much attention to that, but for me it is okay that, say, in case of m rows, we have something like Nico n times Michael log m. If we aggregate, as we have been educated in our, say, middle school, you can easily see that the pseudo-Boolean polynomial is uniquely defined and has some nice properties that doesn't matter which equal values we had in the original input file. We will actually reduce, for this simple example, by 50% the entire set of data. So instead of 20 monomials, taking non-zero 18, and the aggregated data is indicated at the right side. And I would like to explain a little bit more. The term row I will now replace by abstract notion pattern. For me, it doesn't matter how you define the row. And such an example you can see in the top right place, where you see we have resolved the inverse problem. We have found for the aggregated pseudo-Boolean polynomial in the middle written, when we have rearranged such that all terms will be embedded exactly in a similar way when we construct the entire pseudo-Boolean polynomial, and we have actually a matrix which has, say, just 3 columns instead of 5. And the different colors say me how I would, either in the original data or matrix, also doesn't matter how many dimensions will have this matrix, and this y, say, in case of 3 dimensions, might be associated, say, with frontal, horizontal, profile, I don't know, any diagonal, any collection actually of entries might be replaced depending on the application. And this is a very important observation. We also check from some popular benchmark instances in our library, which is well known, Beasley's library. I have no idea where he is. He was with University of London, but now I'm not sure. And famous traveling salesman problem. You can see for Beasley's, say, or instances, the aggregation or say reduction is really essential, at least 80%, and much less, at least 14% for traveling salesman problem instances. Now I'm going to talk about fuzzy reduction. Fuzzy reduction can be done by a simple observation by means of this example. If you have 4 rows or 4 potential places or 4 potential clusters, and we have fixed the number of clusters just by 2, and we know that by zeros we indicate the clusters by means of corresponding Boolean variables which are going to participate in the final answer, then it is clear, say, from a product or term of 3 y's, at least 1 will be 0. So this is actually give us the idea of truncation, and instead of, say, cubic pseudo-Boolean polynomial, you could have, say, quadratic, linear, etc., depending how many clusters we are going to consider. Again, I am not going to spend too much time that, in fact, the truncation operation is also useful, especially for tails, which usually in monotonic behavior of the data per column, not really essential, and doesn't matter. Again, I'm talking about minimization. You can always switch to maximization. It is interesting truncation property which might be used for pre-processing. It means that after truncation, the pseudo-Boolean polynomial, if you look back at the original matrix, the tails will be just equally truncated. And if you ask, for example, for this specific artificially created example, which y's for p equals 3 will be equal 1, it is immediately clear that it will be the third one. Now I'm ready to introduce the equivalent instances. If you have, say, 2 the same size matrices, and we have constructed, as I have described in detail right now, 2 pseudo-Boolean polynomials, we call them these matrices equivalent if they have just exactly the same pseudo-Boolean polynomial. And if it is not the same, by means of the tails, we know that we could truncate what is not really important. For example, if I ask you a question whether these 2 matrices are equivalent and will be aggregated to one of the shapes having just 3 columns, the answer will be yes, because they will have exactly the same pseudo-Boolean polynomial. As usual, for any equivalence, we have properties of reflexivity, symmetry, and transitivity. So we split, or we partition, better to say, the whole data into equivalent classes. And here I am not going into details. When you try to train a DNN network, it is an important question how long we should go through, how many instances. For example, I remind your X-ray pictures 1600. I am sure that it is not necessarily all of them. It is just enough, a few, depending on the range of the original rows representing what you call objects, you know, different which you would like to catch and recognize them. So by this approach, you can easily solve, to our big surprise, the so-called optimal training. So you will never use more, say, pseudo-Boolean different polynomials. The range of matrices will be much more, and I will just in a couple of minutes describe by a polyhedron. Then it is just created randomly, you know, by using empirical objects. How we could create and which kind of operations preserves the equivalence? If we reorder, for example, in this way, as I have done before, so, and they are embedded, so the constant, then the variable with fifth degree, then the term quadratic, etc. In this simple example, cubic, then we could, a lot of operations. We could add extra, say, dummy 0, or we can shift some columns, exchange. We can change the permutations which are not violating the embedding properties, similar like in the Hasse or diagram or in the Boolean. We can rearrange coefficients as we have done by aggregating and finding the most compact representation of the pseudo-Boolean theorem. And now we are very close to answer the following question. What is the minimum number of columns which we could create? And Dolev theorem, if we make a one-to-one correspondence between the terms, or say monomials, the coefficients are not really important, give us an exhaustive answer if we consider a chain, which is by a bold line crossing this Boolean or Hasse diagram. This is nothing else as the sequence of embedded terms. And the question is, how, if you have an arbitrary involved, say, partially ordered sets which are in our pseudo-Boolean polynomial monomials, how we find the minimum number of chains covering all terms? And the answer will be provided by Dolev's theorem, which is saying the minimum number of chains covering all terms is equal to the size of a maximum anti-chain, where anti-chain, in usual sense, this is the maximum number of not embedded terms, or say in partially ordered sets, not embedded subsets. Just to make it clear, for an example, doesn't matter how many you have columns, you can't have less than 6 columns aggregated, and it is clear from Dolev's theorem. It is just, you know, diagonal of the corresponding Hasse diagram. So we can easily introduce equivalence polyhedra. Again, I am not going to spend too much time. For example, if you have fixed the size of the data by which we are going to describe by means of the pseudo-Boolean polynomial, and we remember how we have used the columns, or say matrix of differences and permutations, so we have a very easily created system of equalities and differences which are involved by the corresponding entries and non-negativity of the entries. And finally, we could introduce the polyhedra and solve many additional problems defined on a sequence, or say you can introduce a corresponding basis of the pseudo-Boolean polynomial representing the whole range of equivalent instances. I believe I'm almost done. So we have shown the power of pseudo-Boolean approach to data aggregation, truncation property of pseudo-Boolean polynomial, which reduces the original data within arbitrarily defined, again, rows, where I mean hyperplanes, any collection, as I have shown before, by different colors of patterns. And the number of equivalence classes might be restricted by the nature of their applications. And I am unable, I believe even in a couple of hours, to present not only applications but theoretical questions, how to generalize the creation, the manipulation, even for the three-dimensional matrices, how we are going to use hyperplanes, how we are going to use to combine and to make a precise description of the objects which we are going to recognize or which we are going to apply in different areas. And this just an introductory talk to some applied examples, which tomorrow will be presented by my colleague and PhD student, Tendai Chikaki. I don't see. Tendai, are you here? Oh, hello. So I invite you not to miss these very powerful applications. And I hope, since you have talked today a lot, maybe we will start our collaboration by using this really, in my opinion, elementary and powerful approach to solve some problems. Thank you for your attention and happy birthday to you, Boris. Any questions?
Clarify how you can use this method for classification of images and etc.
Yes, yes.
Just could you
Tomorrow he will talk in details on different examples. I believe four examples you have, different. Maybe you come here just and say a bit more about the examples, but yeah, I invite you.
But essentially the idea that we reduce the size of our matrix and afterwards we apply one of the known algorithms.
Yes. Which kind of algorithm? Here is just you can use linear programming if you would like to describe, say, all equivalent. Of course, you can extend in many ways. You can say, instead of having fixed coefficients in pseudo-Boolean polynomial, you can consider some fuzzy, sets with probabilities, depending on the difference and how wide and well known preliminary information about the object. Image segmentation tomorrow, and I believe much more. I'm not going to replace his talk. Oh, yes.
Do your results imply some new statement about worst-case complexity of well-known problems? Or
you mean for solving the p-median problem? If your question related to the p-median, yes, because just an obvious approach. You should solve online huge sizes p-median problem for clustering, for example, by means of this problem. And you never know what will come, what will be the next one. So you just pre-solve and you create the basis of the pseudo-Boolean polynomial, and when the new instance coming, you just recognize to which of the classes, by means of this equivalence polyhedra, belongs a new instance. That's all.
So is it an NP-complete problem?
The problem is NP-complete. But we have a very powerful, I can say a little bit, and it is a little bit explaining. We have a book which is called Cell Formation in Industrial Engineering, courses with Pardalos and my former PhD student, Professor Dmitry Krushinsky, where we give more examples in cell formation in production.
And this
p-median
problem seems to be a generalization of a minimal transversal of a hypergraph problem.
For example, one of the cases.
So does your method give better worst case complexity? It's sort of intermediate.
Shall I say complexity? No. The problem is
not worst case, but just in
exactly
practical complexity.
practical, much better. Okay. And it is based on two things. I can easily, maybe you remember we had linear terms, constants, quadratic terms, and they are crucial. There are two Humovalas rules which in advance saying when one of the rows should be closed or open. The first rule is trivially obvious. If we haven't any negative, say, coefficients, then it is clear that the first linear term with a, say, 0 or positive coefficient should be just opened or placed to 0. But if we have a negative coefficient, then we sum up all other monomials, in fact, in front of the the coefficients, and we evaluate whether the sum of all coefficients strictly less or more. If it is strictly less, then we just close this, and it is clear that the cancellation from the total contribution to the objective function will be much less. And we use the so-called anti-Humovala branching rule. What it means, it is very simple. Make quadratic term linear. Why? Because when we change a quadratic term, and how we change? Just by branching. We consider which linear term can be cancelled, and one of my students from your department, just a moment, Marko Krasmanovich, I am not sure whether he has completed his study or not. He has shown just one really, in my opinion, good example. All Beasley instances he solved, and they are still in use to show the powerful of different heuristics, and exactly solved with fractions of milliseconds. That's all. You're very welcome. Thank you very much. And I invite you now for conference dinner. And I hope you will follow. Here we have... Я уже перехожу на русский, потому что... Уже можно, наверное, выключать, я же попрощался, да? Я думаю, Владислав нам покажет дорогу. Потому что мы не, я не был там.